Imagine this. A spacecraft, launched before you were even born, is racing through the void of space, 25 billion miles from Earth, farther than anything humanity has ever built. But here's the real kicker. This probe is moving so fast that it would take over 73,000 years to reach the nearest star. It's not just a spacecraft, it's a time capsule, a silent messenger drifting through the cosmic ocean carrying the sounds of Earth, our hopes and our dreams, messages destined for civilizations that may never hear them. But as we stand here on our tiny blue planet, looking up at the night sky, we're left with a question that's as humbling as it is thrilling. How far can we really go? How much do we really know about what lies beyond our solar system, or even beyond the very limits of human imagination? You might think we've reached the edge of the known universe, but that's just the beginning. We're only beginning to grasp the sheer scale of what's out there waiting for us to discover. What if the answers to humanity's most profound questions are hidden just beyond the stars, buried in the unexplored corners of the cosmos? What if we could harness the energy of a star, send our consciousness across the universe, or travel faster than light itself? The truth is, space isn't just a void between stars, it's an untapped frontier filled with unimaginable possibilities and untold dangers. Buckle up, because what we're about to uncover will change how you see our place in the universe forever. Prepare to journey far beyond what you know, into the realm of the unknown. This isn't just about rockets and distant planets, it's about the future of humanity, the next steps in our evolution, and what it will take for us to survive the vast cold darkness between the stars. This is a journey unlike any other, and it starts right now. Our solar system, the familiar domain where we have spent our entire existence, is not the edge of the universe, it's only the beginning. For centuries we've believed that once we reach the outer reaches of our cosmic neighborhood, we had seen everything. Pluto was once considered the last frontier, a distant ice ball at the edge of our known world. Yet even that faraway place wasn't the end. Beyond Pluto there's a boundary that very few of us have even heard of, let alone imagined. The heliport. It's an invisible line, a literal edge of our solar system, marking the point where the solar wind, the charged particles constantly streaming from the sun, loses its power and gives way to the forces of interstellar space. It's a boundary so far out in space that the light from our sun, which seems to rule over everything we know, takes 16 hours just to reach it. Now, let that sink in for a moment. 16 hours? That's how long it takes for sunlight, moving at a speed of nearly 300,000 kilometers per second, to travel to a point that lies roughly 11 billion miles from Earth. And if you tried to drive a car at 60 miles per hour without stopping, you'd need a staggering 12 million years just to get there. This vast distance is beyond the reach of any journey we've ever conceived of, beyond even the most ambitious exploration projects. Yet it marks only a fraction of the true scale of space. The edge of our solar system, the point where our sun's influence finally dies, is an arbitrary line, an invisible border drawn not by anything we can touch or feel, but by the very forces that govern our solar system's existence. Beyond that line lies a completely new world, one where everything we know about time, space, and the universe as a whole is upended. The sun, the center of our solar system, is essentially a massive ball of burning hydrogen and helium that releases incredible amounts of energy, most of which we experience as sunlight. That energy doesn't just light up our days or give us warmth. It also drives something we call solar wind, a constant stream of charged particles. This solar wind pushes outward, creating a protective bubble around us known as the heliosphere. The heliosphere is like an invisible shield that extends well beyond Pluto and protects us from the harsh, high-energy particles that fill interstellar space. This is the space where our solar system's influence dominates, where our sun is the center of everything. But like all things in the universe, even the sun has limits, and eventually that protective wind weakens and vanishes into the interstellar void. The point where that happens is the heliport. The helipause is essentially the boundary where the solar wind from our sun gives way to the fierce winds of interstellar space. It marks the place where the sun's reach fades into nothingness, and the cosmic forces of other stars take over. Imagine for a moment, standing on the edge of that boundary, looking out at a place where no human has ever set foot. The sun's radiation becomes irrelevant, and the protection from deadly cosmic radiation disappears. In this zone, the temperature drops to nearly absolute zero. Space is now not only cold, but it's also a place where the very atoms that make up the universe itself begin to change. This boundary is where the rules of physics start to behave differently, and where our understanding of space, time, and our place in the universe begins to get truly weird. It's a realm where, for the first time, we are no longer sheltered by our sun's influence, and everything we've come to understand about the universe gets thrown into question. In 2012, Voyager 1, launched in 1977 to explore the outer planets, made history by crossing this very boundary. When it did, it became the first human-made object to enter true interstellar space, a feat so monumental that we can hardly grasp the significance. Voyager 1 didn't just leave behind the planets we know and the vast reaches of our solar system. It passed into a new realm, a place where no spacecraft had ever ventured before. The signals it sends back to Earth now take more than 21 hours to reach us. That's longer than a full day. And as the spacecraft continues to move further into the vast emptiness of space, it continues to send us whispers from the unknown, messages from a place that remains largely a mystery. Scientists are still trying to decipher these signals, trying to understand what they mean for our understanding of the universe and what they can teach us about what's truly out there. But here's the part that will truly blow your mind. This edge of our solar system, the boundary where our sun's influence fades, is still less than a 110,000th of the distance to our nearest neighboring star. Think about that. We've sent a spacecraft further than anything humanity has ever launched, and yet, it's still barely begun its journey to the stars. Imagine taking a single step on a journey that would circle the Earth 2.5 million times. That's how far we've come compared to how far we need to go. The helipause isn't just an edge. It's a milestone. It's the first step toward the stars, and yet it's the tiniest fraction of the journey we need to make. It's like we've reached the edge of the Earth, but the next step takes us into the unknown, into a realm so vast that we can't even begin to fathom the distances involved. Standing at the edge of this cosmic shore, we realize something profound. Leaving the solar system is not just about building faster spacecraft or developing better technology. It's about becoming something entirely new, a species that can survive in the cold, inhospitable vastness between the stars. It's about transforming ourselves into explorers, not just of distant planets, but of the very fabric of the universe itself. But here's the thing, our first visitors to this strange realm, our spacecraft like Voyager 1, have already begun sending back the answers we need. These probes, now drifting silent and alone through space, are humanity's ambassadors to the stars. They are our first messenger, carrying with them golden records, the sounds of Earth, the music of whales, the laughter of babies, and even the messages from our cultures, all encoded on golden records, traveling through space at unimaginable speeds, hoping to reach distant civilizations that may never hear them. Yet, as we look to these pioneers, these golden ambassadors, we realize that they are far from immortal. They are slowly dying. Their nuclear power is running out. The machines that have carried humanity's hopes across the universe are fading, one by one. But even as they start to fail, they've already revolutionized our understanding of what lies beyond. Voyager 1 and its sibling Voyager 2 have detected magnetic fields twisted into impossible shapes by the winds of distant stars. They've measured cosmic rays from explosions that happened before Earth even existed. And most shockingly, they've shown us that interstellar space isn't empty. Far from it. In fact, it's filled with a thin soup of hydrogen atoms and mysterious particles from the very birth of the universe itself. It's like a cosmic fog, a space between the stars that is both eerie and alien. It's this hidden, silent realm that our spacecraft are now slowly passing through, sending back valuable data that might one day unlock the true secrets of the universe. But this is just the beginning. As we stand here, looking up at the stars, we realize that Voyager 1 isn't just a machine. It's a symbol of what we as humans are capable of. It's a reminder that we are a species that has already done the impossible, and it's proof that our journey into the stars is just beginning. It's a cosmic message, sent not just to any potential alien civilizations out there, but also to ourselves. The real question isn't whether we can reach the stars, but whether we will have the courage, the technology, and the resilience to survive long enough to do it. Because, as we've seen with the Voyagers, this journey is not just about technology, it's about survival, and it's a journey that has only just begun. As we stand at the edge of our solar system, looking beyond the familiar boundaries of our planets and their moons, we begin to realize how much we've taken for granted. The vast expanse of space that stretches out before us is not a simple empty void. but a realm that is as hostile as it is awe-inspiring. Beyond the helipause, the boundary where our sun's solar wind finally fades into the cold emptiness of interstellar space, there is a dramatic shift. We've talked about the heliosphere, this invisible bubble that has shielded us for billions of years, keeping out the chaos of interstellar radiation and particles. But now, for the first time, we'll leave that protective bubble behind, venturing into a new world entirely, one where the forces of nature are not influenced by our sun. What lies beyond that invisible line? What happens when the gentle warmth of our sun, a constant source of life and light, becomes nothing more than a distant memory? The region of space beyond the heliopause is a place of extremes. It's not just an empty void, it's a cosmic wilderness, a place of tremendous complexity and danger. Imagine the sudden jarring contrast between the familiar warmth of our sun and the frigid, hostile environment that lies just beyond. In the heliopause, our solar wind, the stream of charged particles constantly streaming outward from the sun, has been slowing, unable to maintain its grip against the fierce pressures of interstellar space. Once this solar wind reaches its limit, it gives way to the powerful forces at play in the interstellar medium. It's as if you've stepped from a warm room into the freezing winds of a blizzard, a sudden, shocking change that reminds you just how small and fragile we really are in the grand scheme of the universe. What is interstellar space really like? It's not what you might expect when you think of the word empty. It's not a simple, silent void devoid of anything. Far from it. In reality, interstellar space is filled with an incredibly thin mix of hydrogen atoms, cosmic dust and radiation left over from the Big Bang. The very fabric of space itself is littered with ancient particles, remnants of the creation of the universe itself. These particles are barely detectable by our instruments, yet they are the building blocks of the universe, waiting to be unlocked by the technologies of the future. This soup of particles, although faint, plays an incredibly important role in shaping the interstellar medium, which is anything but empty. It is far from devoid of life and activity, even though we cannot yet fully understand the forces at play. However, one of the most significant features of interstellar space is its vast emptiness, and I don't mean that in the literal sense. What I mean is that, when you leave the bubble of our solar wind, you step into a place where everything becomes even more distant, more isolated. The distances between stars are unimaginable, on a scale that challenges every human instinct for grasping size and scale. If you were to shrink our entire solar system down to the size of a marble, our nearest star, Proxima Centauri, would be a marble's throw away, about 1,000, and that's just our closest neighbor. The stars that make up our galaxy are scattered across a vast, dark ocean of space, with vast stretches of nothingness between them. These distances are so staggeringly large that the notion of interstellar travel, at least with today's technology, feels like an impossible dream. Yet, despite the distances and the vast emptiness between the stars, space is far from static. The interaction between the stars, the particles scattered between them, and the gravity that holds everything together, creates a dynamic and volatile environment. In interstellar space, space itself doesn't behave like it does within the protective bubble of our solar system. The physics change, and even time itself begins to bend under the extreme conditions of this dark abyss. Stars are born, die, and explode, sending shockwaves of radiation and particles through the cosmos. Every few million years, supernovae, a star's dramatic and violent death, create massive explosions that can alter the surrounding environment. These stellar remnants and their deadly radiation reach us even from far-off distances, traveling through space at incredible speeds. In many ways, interstellar space is a cosmic battlefield, where remnants of dying stars create a hostile environment, littered with the dangerous byproducts of their explosive deaths. These forces, invisible yet pervasive, can threaten our spacefaring missions in ways we can't fully comprehend yet. Without the magnetic field of Earth or the sun's solar wind to protect us, space radiation becomes a major problem. We are constantly bombarded with high-energy cosmic rays that, if we're not careful, can overwhelm our spacecraft systems or be deadly to human health. Radiation, both from the remnants of dead stars and cosmic particles traveling at near light speed, is one of the most significant challenges we must overcome to explore this alien realm. Yet, even in the face of these dangers, humanity is beginning to push its boundaries. Voyager 1, the first human-made object to leave the protective influence of our solar system, is racing ahead into the unknown. As it crosses the boundary into interstellar space, It sends back faint signals that allow us to glimpse the mysteries of the universe beyond. The signals that Voyager sends take more than 21 hours to reach us, a chilling reminder of just how far it is from home. Yet, in those faint whispers, we're learning more about the makeup of interstellar space than we ever thought possible. These signals contain invaluable information that our scientists are still processing and analyzing, trying to decode the messages from deep space. In the vast empty darkness of interstellar space, humanity's greatest achievements are just beginning. Our spacecraft, while small and fragile compared to the vastness of the cosmos, are now our ambassadors to the stars. The golden records carried by Voyager 1 and Voyager 2, messages from Earth encoded on gold-plated discs, are proof of our desire to connect with something greater than ourselves. These records carry sounds from our planet, whales singing, babies crying, and music from every corner of the world, like a cosmic message in a bottle sent out into the infinite dark. These records may travel for millions of years before they are discovered by any alien civilization, if they are ever found at all. But even if they are never discovered, the act of sending them out into the void is symbolic of humanity's eternal quest for knowledge, understanding, and connection. Yet, even as we send these messages out into the stars, we are also faced with the very real dangers of the void. As Voyager 1 continues its journey deeper into interstellar space, we are reminded of just how fragile our technology is. Despite its incredible longevity, lasting far longer than anyone could have predicted, Voyager's nuclear heart is slowly dying. Its power source is gradually losing its ability to send signals back to Earth. The spacecraft is aging, its systems are failing, and the messages it carries are growing weaker with every passing year. By 2025, Voyager 1 will fall silent forever, its radio signals extinguished as its power supply finally runs out. But even in its final moments, Voyager will continue to represent something far more profound than just a machine. It symbolizes humanity's desire to explore, to reach out into the unknown, and to leave a mark on the universe that will outlive us. It's a testament to the resilience of human ingenuity, to the spirit of discovery that pushes us beyond the limits of what is possible. And although the probe itself will eventually fade into the darkness, the knowledge it has already given us will shape our future for generations to come. As we venture further into the darkness, we must grapple with the question, how do we survive this vast, empty expanse? How do we, as a species, continue to exist when faced with the unimaginable distances, the deadly radiation, and the harsh conditions of interstellar space? The answer lies in our ability to adapt, to innovate, and to continue pushing the boundaries of human exploration. What lies beyond the heliopause is a challenge, a realm of untold dangers and unimaginable beauty. But it's a challenge we are beginning to meet head-on, one spacecraft at a time. It's a reminder that we are still only at the very beginning of our cosmic journey. Beyond our sun, beyond the planets and their moons, lies a universe of unimaginable scale, filled with mysteries waiting to be unraveled. And though the distance is vast, though the darkness seems infinite, we are already taking the first steps toward reaching it. With each spacecraft we send out, with each new discovery we make, we move ever closer to understanding our place in the universe, and perhaps one day to becoming a true spacefaring species, capable of surviving and thriving in the cold, dark expanse of the stars. The journey is long, but the adventure is only just beginning. Beyond the edge of our solar system lies a realm so foreign, so uncharted, that it seems almost impossible to imagine. We often think of the universe as a vast emptiness, a dark ocean between the stars. But in reality, this space, though seemingly void of anything recognizable, is teeming with activity, albeit at a scale that challenges human comprehension. The moment we leave the protective bubble of our solar system, we're thrust into a zone where every rule we've come to understand about space-time, physics, and even the nature of the universe itself starts to shift. It's not just that we're leaving the comfort of what we know, it's that we're entering a completely different realm of existence, one where the forces of nature are unpredictable, and the laws of physics we take for granted don't always apply in the way we expect. The journey from our solar system into interstellar space, though vast, represents humanity's first steps into a place where space is not just empty, it is alive with complex interactions that we are only beginning to understand. Beyond the heliopause, that invisible line that marks the end of the solar wind's reach, we enter into what scientists call the interstellar medium, a diffuse, low-density soup of gas, dust and radiation that spans the space between the stars. It's not an empty vacuum as we often imagine. In fact, this medium is filled with atoms and particles left over from supernovae and the birth of the universe itself. These particles drift through space at speeds unimaginable to the human eye, interacting in ways that scientists are still unraveling. And while this interstellar space might seem cold and lifeless, it plays a critical role in the ongoing evolution of the cosmos. Perhaps the most surprising revelation of interstellar space is that it's not, in fact, empty at all. It's filled with a thin but constant stream of hydrogen atoms, the building blocks of stars and planets, traveling at incredibly high speeds. These hydrogen atoms are remnants of the Big Bang, ancient echoes from the very birth of the universe. As they travel through space, they interact with cosmic radiation, creating the background noise that permeates the cosmos. This cosmic background radiation, although faint, is crucial in understanding the origins and evolution of the universe. It's a key puzzle piece in the cosmic story, one that we're still trying to fully piece together. However, it's not just the hydrogen atoms that define the interstellar medium, it's also the powerful magnetic fields that stretch between stars. These fields, created by the movement of charged particles through space, are not just passive observers in the vast emptiness. They actively shape the flow of matter and energy through the universe. Imagine, if you will, a silent current flowing through the cosmic sea, guiding and pushing the particles of interstellar space in ways that we're only beginning to comprehend. These magnetic fields connect the stars in a cosmic web, creating invisible pathways that guide the movement of matter across vast distances. The energy from these magnetic fields can bend space-time itself, subtly affecting the motion of stars and planets, and even altering the very fabric of the universe. The interaction of these cosmic elements, the hydrogen atoms, cosmic dust, and magnetic fields, creates a unique environment for exploration. But this environment is far from forgiving. When humanity's first spacecraft, like Voyager 1, began their journey into the interstellar medium, they faced a number of challenges that scientists hadn't fully anticipated. One of the first obstacles they encountered was the increase in cosmic radiation. Without the shielding of the Earth's magnetic field or the solar wind's protective push, spacecraft venturing beyond our solar system are bombarded by radiation from distant stars, supernovae, and other cosmic sources. This radiation can damage sensitive electronics and threaten the safety of human travelers. For a spacecraft to survive in this hostile environment, it must be built to withstand not only the extreme conditions of space, but also the unpredictable and powerful forces at play in the interstellar medium. Beyond the radiation, another danger lies in the cosmic dust and particles that populate interstellar space. These particles, though small, travel at speeds that can reach up to several hundred kilometers per second. At such velocities, even the smallest piece of space dust can be deadly. If a spacecraft were to collide with one of these particles, the damage could be catastrophic. The force of impact at such high speeds would be enough to pierce through metal, damage delicate instruments, and potentially even cripple a mission. Yet, this is just one of the many threats that humanity will need to overcome if we hope to venture further into the interstellar realm. The challenge of building spacecraft that can survive the harshest conditions of space is a monumental task that requires not only advanced technology, but also a deep understanding of the forces at play in the cosmos. But it's not just the immediate dangers of interstellar space that we must consider. As we push further out into the void, we are confronted with the existential question of our survival. The vast emptiness between the stars, while not completely devoid of matter, is still incredibly distant and isolated. The closest star to our own, Proxima Centauri, lies more than 4 light-years away, a distance so great that it would take our fastest spacecraft like Voyager 1 tens of thousands of years to reach it. Even with the most advanced technology we can currently imagine, interstellar travel is still a distant dream. The energy required to travel such vast distances is beyond anything we've ever conceived of. To move at a fraction of the speed of light, we would need to harness the energy of an entire star, an unimaginable feat with today's technology. Yet, despite these daunting challenges, the allure of exploring interstellar space is undeniable. The possibilities that lie beyond our solar system are tantalizing. What if there are other planets, other stars, that could support life? What if we could one day colonize distant worlds, ensuring the survival of humanity long after Earth has ceased to exist? The potential for discovery is limitless, and it's this very potential that drives our desire to reach beyond the stars. As we continue to explore the interstellar medium, we must ask ourselves what we are truly seeking. Are we simply searching for new frontiers, Or are we looking for something deeper, a greater understanding of our place in the universe? As we push further into this vast unknown realm, we begin to realize that the journey is just as important as the destination. The act of exploration itself, the quest to understand the universe and our role within it, is what defines us as a species. It is our curiosity, our drive to reach beyond the known, that will propel us forward into the future. Yet, even as we venture further into the dark abyss of space, we must remain grounded in the reality of our situation. The challenges of interstellar travel are not just technical, they are deeply existential. The distances involved are so vast that they push the boundaries of human understanding. We are faced with the very real possibility that our efforts to explore beyond our solar system may take centuries, if not millennia, to bear fruit. The technological and logistical challenges are immense, and yet the desire to continue is unyielding. The fact that we are already sending spacecraft into the interstellar medium, exploring the very fabric of space itself, is a testament to the resilience of the human spirit and our unrelenting curiosity about the world beyond. In the end, as we continue to push further into interstellar space, we are not just exploring the cosmos, we are exploring ourselves. The journey to the stars, with all its dangers, complexities, and uncertainties, is a reflection of the human drive to push beyond the limits of what is known and venture into the unknown. It's a journey that may take generations to complete, but it is a journey that humanity must embark on if we hope to understand our true place in the vastness of the universe. And as we look to the stars, we realize that the future of humanity lies not just in the survival of our species, but in the pursuit of knowledge and the desire to explore the unknown, no matter how far or how difficult the journey may be. As we leave the familiar comfort of our solar system behind, venturing into the vast and uncharted territories of interstellar space, a sobering realization begins to set in. Humanity's survival in this cosmic wilderness will not come easily. The very nature of space beyond our solar bubble is unforgiving. No longer protected by the magnetic fields of our Sun or Earth's atmosphere, our spacecraft are thrust into an environment so alien that the laws we understand and rely on, those that guide our daily lives on Earth, start to lose their meaning. As our probes journey deeper into this dark unknown, we are learning that surviving in this hostile space, let alone thriving, will require us to rethink everything we know about human exploration and what it means to travel between the stars. The reality of interstellar space is not just the emptiness, the cold silence, or the crushing distances that separate us from our nearest star. No, what we face as we venture further from Earth is a battleground of natural forces so potent that even our most advanced technology, our greatest scientific achievements, are but fragile sparks in the face of cosmic turmoil. Even more daunting is the knowledge that we are only beginning to understand the true scale of these challenges. It's one thing to design a spacecraft capable of reaching the edge of our solar system, but quite another to imagine a mission that crosses the gulf between stars. The energy required, the survival of the technology, the duration of the journey, and the physiological and psychological toll on human beings, all of these challenges are far beyond what we've ever encountered. First and foremost, we are confronted by one of the most dangerous aspects of interstellar space: radiation. Throughout our solar system, the sun's powerful magnetic field, coupled with the solar wind, creates a protective shield known as the heliosphere, which keeps us safe from the majority of cosmic radiation that fills the universe. But as we journey past the edge of this bubble, into the uncharted expanse of the interstellar medium, we are no longer protected by the sun's magnetic field. What's more, the radiation that fills interstellar space is far more intense and dangerous than anything we experience within our solar system. In this dark expanse, we are bombarded by high-energy cosmic rays, particles moving at nearly the speed of light, originating from distant supernovae, black holes, and other stellar phenomena. These cosmic rays are capable of penetrating even the most sophisticated shielding, and the damage they can inflict on spacecraft electronics is devastating. While spacecraft like Voyager 1 have survived for decades, sending back data from the edge of the solar system, this success is not a guarantee for future missions, especially those that venture further into interstellar space. The technology we currently rely on, despite its remarkable longevity, is ill-equipped to withstand the unrelenting onslaught of cosmic radiation that would increase exponentially the further we travel from the sun. More than just electronics, cosmic radiation presents a grave threat to the safety of any human crew that might one day undertake a similar journey. The biological effects of radiation exposure in space are a well-documented concern. Radiation can damage human DNA, leading to a variety of illnesses, including cancer, genetic mutations, and neurological disorders. In space, the risk of exposure is far higher than on Earth, where our atmosphere and magnetic field offer natural protection. Without these defenses, astronauts would be vulnerable to radiation at every step of the journey. Long-term exposure to this radiation is one of the greatest hurdles humanity must overcome in order to survive interstellar travel. Current radiation shielding, while effective in low Earth orbit or around the Moon, would be woefully inadequate for the journey to another star. Even with advanced technologies, it is unclear how we can protect human life over the course of decades or even centuries of exposure to cosmic radiation. This brings us to another critical challenge: time. As we venture further from the Sun, we are confronted with the most daunting of all obstacles: the sheer scale of the distances involved. Even the fastest spacecraft ever built, Voyager 1, traveling at over 38,000 miles per hour, would take tens of thousands of years to reach the nearest star, Proxima Centauri. This stark reality forces us to confront the limitations of our current technology. The idea of reaching another star within a human lifetime is, at present, a fantasy. To even begin to make interstellar travel possible, we would need to radically rethink the way we design spacecraft, develop propulsion systems, and harness energy. But this is where the imagination of scientists, engineers, and visionaries comes into play. Over the years, numerous concepts have been proposed for faster-than-light travel. While many of these ideas currently exist only in the realm of theory, they open the door to the tantalizing possibility that we may one day transcend the limitations of our current propulsion systems. Concepts like the Alcubierre drive, the theoretical faster-than-light warp drive, offer a glimpse into a future where space itself could be manipulated to allow for travel beyond the speed of light. The idea is simple in theory. Instead of traveling through space at sublight speeds, we could warp space-time itself, contracting it in front of us and expanding it behind us, moving us from one point to another faster than light could travel through the space in between. While the science behind such concepts is still speculative, the very fact that physicists like Miguel Alcubierre have formulated a mathematical framework for faster-than-light travel is an exciting development. If we can one day unlock the mysteries of space-time, interstellar travel might not just be a dream, it could be an inevitable leap for humanity. But to get there, we need breakthroughs in both physics and technology that are beyond our current understanding. The idea of warping space-time is based on Einstein's general theory of relativity, but it requires the manipulation of negative energy, something that has yet to be proven possible. In essence, we need to learn how to bend the very fabric of space and time to achieve the unthinkable. Even if we don't yet have the means to travel faster than light, there are still other options worth exploring. For instance, the idea of using nuclear propulsion, such as in the Project Orion concept, could allow us to travel at a fraction of the speed of light. Project Orion proposed using nuclear bombs to propel a spacecraft forward, detonating a series of nuclear explosions behind the ship to push it through space. Although the concept has never been realized, its scientific principles were sound, and nuclear propulsion could provide the immense thrust needed to push a spacecraft to speeds that are orders of magnitude greater than current chemical rockets. But even nuclear propulsion has its limitations. The energy required to propel a spacecraft at even a small fraction of the speed of light is immense. A single trip to the nearest star would require energy resources that would dwarf anything we've ever harnessed. The sheer scale of the energy requirements raises another significant obstacle. How do we generate and store such massive amounts of energy? Our current methods of generating energy through chemical reactions, nuclear fission, or even solar power are insufficient to meet the demands of interstellar travel. The search for alternative energy sources, such as antimatter or fusion, will be critical to making interstellar missions a reality. Yet, despite all these challenges, there is a spark of hope. The development of new technologies, the refinement of our understanding of space, and the discovery of new energy sources may one day make interstellar travel possible. But to get there, we will need to think beyond the boundaries of our current knowledge, pushing the limits of human ingenuity and imagination. The road ahead will be long, but it's a road that must be traveled if humanity is to explore the stars and ensure its place in the future of the cosmos. In the end, the journey to the stars will not be just a technical achievement. It will be a test of human endurance, resilience, and determination. The obstacles we face are daunting, but they are not insurmountable. If we can overcome the challenges of radiation, time, and energy, we will unlock the secrets of the universe and open the door to a future where humanity is not confined to a single planet, but spreads its wings across the stars. It will be a journey that will take generations, but it's a journey that humanity must undertake. The cosmos is waiting, and it's calling to us, urging us to take the first steps into the vast unknown expanse beyond our solar system. As humanity's exploration of interstellar space continues to evolve, it's becoming increasingly clear that the challenges we face are not just technical or logistical. They are philosophical. We are venturing into the great unknown, a realm that promises both incredible discoveries and unimaginable risks. The harsh reality of space beyond our solar system forces us to confront some of humanity's most profound questions. What is our place in the universe? How far are we willing to go to ensure the survival of our species? And perhaps most importantly, what are we truly seeking among the stars? At the core of interstellar exploration lies one of humanity's oldest and most enduring aspirations, the search for life. For centuries we have looked to the stars, wondering if we are alone in the universe, or if other civilizations have already risen and fallen in the vast stretches of space. Our curiosity is driven by a deep-seated need to understand whether life exists beyond Earth, and if so, what it might look like. But the search for extraterrestrial life is far from simple. It's not just about finding life, it's about understanding the conditions that might support it, and how we might one day thrive in environments far different from the one we've always known. The idea that life could exist elsewhere in the universe is not a new one. For centuries, astronomers and scientists have speculated about the possibility of alien worlds, planets orbiting distant stars that could harbor life in some form. With the discovery of thousands of exoplanets in recent years, the possibility of finding habitable worlds beyond our own has moved from the realm of speculation to something much more tangible. Today we know that there are potentially billions of Earth-like planets in our galaxy alone, planets that exist in the so-called Goldilocks zone, where conditions might be just right for liquid water to exist, one of the key ingredients for life as we know it. This discovery is a game-changer. For the first time in history, humanity is on the brink of answering one of its oldest questions. Are we alone in the universe? And while we have yet to find definitive evidence of extraterrestrial life, the mere possibility that life exists elsewhere has profound implications for the future of human exploration. If we are ever to travel to another star, we may very well find worlds that harbor life, worlds that could hold the key to understanding the origins of life itself, and perhaps even the future of our own species. But finding life beyond Earth is not just about discovering something new and exciting. It's about ensuring the long-term survival of humanity. As we look to the stars, we are not just seeking new knowledge or new worlds to explore. We are seeking a backup plan, a way to preserve humanity and its culture in the face of existential threats. We know that Earth, despite its beauty and abundance, is not a permanent home. Whether due to natural disasters, climate change, or the eventual death of our sun, the survival of humanity on Earth is not guaranteed. In fact, the likelihood of a global catastrophe occurring in the future is high, and while we can take steps to mitigate certain risks, the ultimate survival of our species depends on our ability to venture beyond Earth. This realization has driven some of the most ambitious space missions in history. Scientists and engineers are working tirelessly to develop the technologies that will enable us to travel to distant stars, to colonize other planets, and to create new homes for humanity. One of the most promising candidates for such a future is Proxima Centauri, the closest star to our own sun, located just over 4 light-years away. Proxima Centauri is a red dwarf star, much smaller and cooler than our sun, but it holds one key feature that makes it a candidate for potential colonization. It has a planet, Proxima b, that resides within its habitable zone. Proxima b, with its potential to support liquid water, has become a focal point for those envisioning humanity's future in the stars. It is far from perfect. The planet is constantly bombarded by intense radiation from its parent star, which has frequent solar flares, yet the very fact that it exists in the habitable zone makes it a candidate for exploration. If we can overcome the challenges of radiation and develop the technology to protect human life during a journey that could take decades or even centuries, Proxima b may one day serve as a second home for humanity. This concept of colonizing distant planets is not just a pipe dream, but a necessity for the future survival of the human race. But venturing to Proxima Centauri or any other star is not without its own set of challenges. First, the technological hurdles are immense. Even with our current advancements in propulsion systems, it would take us tens of thousands of years to reach Proxima Centauri with conventional methods. Our fastest spacecraft, Voyager 1, travels at a speed of about 38,000 miles per hour, and at that speed it would take over 70,000 years to reach our closest neighbor. To overcome this challenge, we would need to develop new propulsion systems that can travel at a significant fraction of the speed of light. Concepts like the Breakthrough Starshot project, which aims to send small lightweight spacecraft to Proxima Centauri using powerful lasers, could shorten the journey to a matter of decades. But even this technology is still in the early stages of development. Then there are the challenges of sustaining life on a multi-generational voyage. The journey to Proxima Centauri could take several generations to complete, and that means humanity would need to develop spacecraft capable of supporting entire civilizations during these long journeys. A generation ship, an enormous vessel that would carry people, animals, and plants for hundreds of years, would need to be completely self-sufficient. It would need to produce its own food, recycle air and water, and generate energy for the duration of the journey. The psychological and social challenges of living aboard such a ship are profound. How would future generations on board a generation ship maintain their motivation and purpose? How would they cope with isolation from Earth and the knowledge that they would never see their home planet again? These challenges are not insurmountable, but they require an unprecedented level of cooperation and ingenuity. As we push further into the stars, we will have to come to terms with the fact that the journey itself will be as much a test of humanity's resilience and adaptability as it will be a technological challenge. The ability to live and thrive in space, to build communities and sustain life for generations, will be the true measure of our success. And while the prospect of interstellar travel remains distant, the technologies and knowledge we gain along the way will have far-reaching implications not only for space exploration, but also for life on Earth. The search for life beyond Earth and the quest to ensure humanity's survival are not mutually exclusive. They are deeply intertwined. As we reach for the stars, we are not just looking for alien life, we are looking for ways to ensure that life itself, our life, can continue long after Earth has run its course. Whether we are sending probes to distant stars or dreaming of colonizing new worlds, the ultimate goal is the same: preserve humanity and its achievements for future generations, no matter where in the cosmos they might be. The challenge, of course, is not just technical but philosophical. As we venture deeper into space, we will be forced to ask ourselves what it means to be human. What are we willing to sacrifice in the pursuit of survival? How far are we willing to push the boundaries of science and technology to ensure our species thrives across the universe? The answers to these questions will shape not only the future of space exploration, but also the future of humanity itself. As we look to the stars, we realize that the journey we are embarking on is as much about our own survival as it is about the pursuit of knowledge and discovery. This quest for life, for survival, and for understanding is what drives us forward. It is what has always driven us as a species: an unyielding curiosity, an insatiable thirst to understand the world around us, and a deep-seated desire to reach beyond our limits. And while the stars may seem impossibly distant, we are moving closer every day. The technologies we develop, the questions we ask, and the answers we find will not only unlock the secrets of the universe, but will also illuminate our path forward into the future. A future where humanity's destiny is not confined to one planet, but spread across the stars. As humanity stands on the brink of its most ambitious journey yet, interstellar travel, we are faced not only with the monumental technological challenges of reaching other stars, but also with profound philosophical and existential questions that touch upon the very nature of our species. In the uncharted depths of space, where time and distance are stretched to unimaginable scales, we are forced to reconsider our understanding of life, survival, and what it means to be human. The barriers to interstellar travel are not merely physical, they are deeply tied to our ability to adapt, innovate, and transcend the limitations that have defined us for millennia. One of the most pressing challenges we must confront as we prepare to venture into the stars is the question of how to survive the long, treacherous journey. The journey to the nearest stars, Proxima Centauri, for example, could take decades, even centuries. Unlike the relatively short trips we make to the Moon or Mars, interstellar travel will demand a radically different approach to life support, energy production, and long-term sustainability. Human civilization will need to become not just spacefaring but self-sustaining, capable of surviving in the most hostile environment imaginable: the cold, dark void of space, far from the warmth and protection of Earth. At the core of this challenge is the issue of energy. In the vacuum of space, there are no natural sources of energy to harness, as we can on Earth. Our sun, which provides life-sustaining energy for everything on our planet, is distant and irrelevant in the vast emptiness between the stars. To embark on an interstellar journey, we would need to develop new methods of energy generation, methods that are far more efficient and powerful than anything we currently have. This might involve harnessing the power of nuclear fusion, antimatter, or even exotic energy sources that we have yet to fully understand. Nuclear fusion, the process that powers the stars themselves, holds the promise of being the energy source that could propel us across the stars. Unlike nuclear fission, which splits atoms to release energy, fusion combines atomic nuclei to form heavier elements, releasing enormous amounts of energy in the process. This is the same reaction that powers our sun, and if we could replicate it on a spacecraft, it could provide virtually limitless energy for a journey to another star. Yet, despite decades of research, nuclear fusion remains tantalizingly out of reach. While we've made strides in experimental fusion reactors, creating a reliable and sustainable fusion engine capable of powering spacecraft is still a distant dream. In the meantime, we must also consider other sources of energy, such as antimatter. Antimatter is the opposite of normal matter, consisting of particles that have the opposite charge of the particles we're familiar with. When matter and antimatter collide, they annihilate each other in a burst of energy so intense that it defies the imagination. Antimatter is currently produced in extremely small quantities in particle accelerators, and while its potential as an energy source is staggering, it is still many orders of magnitude away from being usable in the quantities required for interstellar travel. The challenge of creating, storing, and efficiently utilizing antimatter for propulsion is one of the greatest obstacles that scientists and engineers must overcome. As we think about the journey ahead, we must also grapple with the question of what kind of spacecraft will be required to carry humanity across the stars. Current spacecraft are designed for relatively short missions, such as trips to the Moon or Mars, but to travel to another star, we would need a ship, unlike any that we've built before, an enormous vessel capable of sustaining life for generations. This is where the concept of generation ships comes into play. A generation ship is a massive spacecraft designed to support entire communities for the long journey between stars. Unlike conventional spacecraft, which are designed for short-term missions, a generation ship would be self-sustaining, with the ability to recycle air, water, and food indefinitely. Building a generation ship that could sustain a human population for hundreds or thousands of years is no small feat. The ship would need to be equipped with everything necessary to maintain life: farms to produce food, factories to create tools and spare parts, and systems to generate energy and recycle waste. But the true challenge goes beyond the technological. There are social and psychological aspects that must be addressed. A generation ship would be a microcosm of human civilization, isolated from the rest of the universe for centuries. The people on board would not just be travelers, they would be the ancestors of future generations, born and raised on the ship. What kind of society would they form? How would they maintain their sense of identity, purpose, and motivation over the course of such a long journey? In a generation ship, entire families would live and die without ever seeing the destination. The children born aboard the ship would never know Earth, and their descendants would grow up in an environment completely different from the one their ancestors knew. The psychological toll of such isolation could be immense. Social structures would be tested in ways that we can't yet fully predict. Will generations aboard the ship continue to follow the original mission, or will they diverge into new cultures, languages, and belief systems? The isolation of space travel could give rise to new forms of governance, new philosophies, and new identities. Perhaps by the time the ship reaches its destination, the people on board will no longer identify as Earthlings at all. They might see themselves as citizens of a new world, citizens of the stars. To make a journey to the stars feasible, we also need to rethink the nature of human biology itself. How can we adapt to the long-term effects of space travel on our bodies? The lack of gravity, the intense radiation, the isolation, all of these factors will have profound effects on human health. In low Earth orbit, astronauts are already subject to muscle and bone loss, changes to the cardiovascular system, and psychological stress from prolonged isolation. In deep space, these effects would be magnified. To survive long-duration space missions, humans will need to undergo significant biological adaptation. This might include genetic engineering, cryogenic preservation, or even digital consciousness transfer. If humans are to travel to distant stars, we may need to become something different, something more than just the creatures that evolved on Earth. One possibility is the development of cryogenics, or suspended animation. essentially putting human bodies into a state of deep sleep for the duration of the journey. By slowing or halting the aging process, we could avoid the ravages of time and radiation. While this technology is still in its infancy, advances in cryogenics could one day make it possible for astronauts to sleep through the long years of travel to another star. But the challenges of cryogenic preservation are formidable. Freezing human tissue without causing irreparable damage to cells and organs is a scientific hurdle that has yet to be overcome. Moreover, the psychological challenges of being in suspended animation for decades or centuries are just as significant as the physical ones. The human mind may not be able to withstand the disconnection from the world, from loved ones, from all that we know. Alternatively, we could explore the concept of digital consciousness, transferring human minds into machines or computer systems that could travel across the stars. If we could map and replicate the human brain's neural patterns, it might be possible to upload our consciousness into a digital form, allowing us to live in a virtual reality while the body remains frozen in stasis. This would eliminate many of the biological limitations of space travel, but it raises its own ethical and philosophical questions. Would a digital version of a person truly be the same as the original? What does it mean to be human if our consciousness can be separated from our body? The nature of identity and consciousness would be profoundly challenged by this kind of technology. Ultimately, no matter which path we take, whether biological or digital, the question of survival in deep space forces us to confront some of the most fundamental questions about what it means to be human. Can we preserve the essence of our humanity, even when separated from Earth and our familiar surroundings? What does it mean to leave behind everything we know and travel to a distant star, where we may never return, and where the future of our species depends on the survival of those who are born on a spacecraft far, far home? These questions are at the heart of humanity's quest for the stars. The pursuit of interstellar travel is not just about technology or exploration. It is about understanding who we are as a species and where we are headed. It's about pushing the boundaries of what is possible and asking ourselves how far we are willing to go to ensure that humanity's legacy endures no matter how far from Earth it may be. The journey to the stars is a journey of self-discovery, of adaptation and survival, and of embracing the unknown in ways that will define the future of our species for centuries to come. As humanity edges closer to the possibility of interstellar travel, one of the most profound challenges we face is not just the technological and biological hurdles, but the ethical considerations that come with such ambitious endeavors. Interstellar travel, which once seemed like the stuff of science fiction, now lies within the realm of possibility. But that potential comes with deep unanswered questions about the ethics of venturing beyond Earth. What does it mean to leave behind our planet, our home? What moral responsibilities do we have, not just to ourselves and future generations, but to the Earth itself, and perhaps even to any potential extraterrestrial life we may encounter? These questions are not merely academic, they are fundamental to the choices we will make as a species in the coming decades. As we begin to stretch out into the cosmos, we must confront the possibility that our actions in space may alter the course of humanity, for better or worse. One of the first ethical concerns arises with the very idea of interstellar colonization. The concept of settling on distant planets, once seen as a hopeful pursuit of the human spirit, now carries echoes of past colonialism. The idea of expanding human civilization to other worlds is undoubtedly appealing, especially in the face of the existential threats that Earth faces, such as climate change, overpopulation, and the eventual death of our sun. Yet, there is a risk that the colonization of new planets might mirror the darker aspects of Earth's history, where the exploration of new territories was often accompanied by the exploitation and destruction of indigenous populations, ecosystems, and cultures. The ethical question here is not whether we should explore other worlds, but how we do so responsibly. What would it mean to claim a planet? If we discover a new Earth-like world that is capable of sustaining human life, should we simply settle there? Or should we recognize that these planets too may have their own forms of life? Life that we may not even recognize or understand. The recent discovery of faintly habitable exoplanets, such as those in the Proxima Centauri system, has reignited this debate. Should humanity have the right to colonize these planets, simply because they are in the habitable zone of a distant star? Or do we have a moral obligation to leave them untouched, allowing any indigenous life, if it exists, to flourish unimpeded by human intervention? The ethical principle that comes into play here is known as the precautionary principle, which suggests that, in the face of uncertainty, we should err on the side of caution. This principle has been a guiding force in environmental policy on Earth, where the potential consequences of human actions on the environment are taken seriously. In the context of space exploration, this could mean taking extraordinary measures to avoid contaminating distant planets with earthly microbes, especially if there is a possibility that alien life exists on those planets. Contamination could go beyond simply the spread of Earth life to other worlds. It could also mean irrevocably changing the ecological balance of a planet, making it unsuitable for the native organisms that may already exist. We already have protocols in place for planetary protection, such as sterilization of spacecraft before sending them to other worlds like Mars. However, the scale of these efforts would need to be greatly expanded for interstellar missions. It's one thing to send a robot to Mars, it's quite another to colonize an entirely new world, potentially impacting the course of its natural history forever. This question of ethics becomes even more complex when we consider the potential discovery of extraterrestrial life. If, during the course of interstellar exploration, we encounter evidence of life, whether microbial or intelligent, the ethical landscape will shift dramatically. What do we do if we find life that is radically different from our own? Do we have the right to interact with it? If this life is microscopic, would we risk bringing harmful Earth microbes that could destroy or disrupt this fragile ecosystem? If the life is more advanced, how do we approach it without imposing our own values or risking the collapse of a potential alien civilization? Could we, as explorers of space, be facing a moral obligation to protect and preserve other forms of life in the universe, just as we strive to preserve life here on Earth? The ethics of interstellar exploration and colonization are also deeply tied to the issue of human rights and governance. If humanity does embark on long-term interstellar missions, particularly those involving generation ships or the creation of colonies on distant planets, we must ask how we will govern these new human societies. If a group of people is destined to live out their lives on a ship or a distant planet, how will they maintain their autonomy and freedom? The power dynamics of such missions, how decisions are made, who has the right to control resources, and how disputes are resolved, will require new forms of governance. These ethical dilemmas are compounded by the reality that the people on these missions will be cut off from Earth for potentially hundreds or even thousands of years. They may never have the opportunity to return to Earth, and their children born in space or on another planet may not even know their ancestral home. Who gets to decide the fate of these new societies? The governance of interstellar colonies also raises the issue of potential exploitation. If we establish colonies on planets or moons in other star systems, will the resources of these new worlds be used for the benefit of a select few, or will they be shared equally among all of humanity? How do we ensure that colonization does not lead to the same patterns of inequality and exploitation that have marked human history on Earth? The challenge here is to create a fair and just system of governance that protects the rights of all individuals, even in the vast isolation of space, where oversight and accountability may be limited. But the ethical questions of interstellar exploration are not confined to distant worlds or the potential discovery of extraterrestrial life. They also touch on the future of humanity itself. As we look toward the stars, we must grapple with what it means to be human in an age when we may no longer be bound to a single planet. Advances in technology may one day allow us to alter the human body and mind in ways that are currently unimaginable. Genetic engineering, cybernetic enhancements, and even the possibility of uploading human consciousness into machines could all radically change what it means to be human. These advancements might allow us to adapt to the harsh conditions of space, but they also pose profound ethical questions. If we can modify our bodies and minds to survive in space, do we risk losing something essential about ourselves in the process? Will we still be human if we transcend our biological form? As humanity expands into space, the very definition of humanity could evolve in ways that we are only beginning to comprehend. And then there is the question of our responsibility to future generations. Interstellar travel is not something that will happen overnight. The first successful missions may take decades to plan and prepare, and the first interstellar journey could last centuries. The decisions made today will affect not only our generation but countless generations to come. How do we balance the pursuit of knowledge and exploration with the duty to preserve our planet and its resources for future generations? How can we ensure that we do not overreach and put future human generations in jeopardy, whether by exhausting our resources, introducing harmful technologies, or leaving behind an unsustainable legacy? These ethical concerns, ranging from planetary protection to human governance in space, to the nature of what it means to be human, are not questions that have easy answers. However, they are questions we must begin to address, as we enter the final frontier of space exploration. As we reach out toward the stars, we must ask ourselves how we can navigate these uncharted territories with responsibility, foresight, and compassion. Ultimately, the question of whether we should explore and colonize the stars is not simply a question of technology or capability. It is a question of humanity's values, our ethical compass, and our ability to ensure that the future we create in space is one that respects the dignity of all life, human and non-human alike. As we look beyond Earth, we must do so with humility, recognizing that our actions in the cosmos will not only shape the future of our species, but also set the course for generations to come. The ethics of interstellar exploration will require us to redefine our place in the universe and the responsibilities that come with being part of a much larger cosmic community. As humanity dreams of reaching the stars, it is impossible to ignore the underlying truths that lie at the heart of any long-term spacefaring venture. The road to interstellar travel is long, fraught with challenges, and, as of now, seemingly insurmountable. And yet, we continue to push the boundaries of what's possible, fueled by the same curiosity that has driven us to explore every corner of our planet and beyond. For all the technological advancements we have made, one of the most formidable obstacles in the quest for interstellar travel is the issue of speed, specifically the speed at which we can travel through the vast expanse of space. The speed limit of the universe, as dictated by Einstein's theory of relativity, is the speed of light, approximately 300,000 kilometers per second. Nothing in the universe can travel faster than this speed, which creates an immense challenge when thinking about interstellar travel. Even at the speed of light, it would take over 4 years to reach Proxima Centauri, the closest star to our own. At our current technological capabilities, using even the fastest spacecraft ever made, Voyager 1, which travels at around 38,000 miles per hour, it would take tens of thousands of years to reach the nearest stars. The question then becomes not whether interstellar travel is possible, but how we can break through these fundamental constraints of space and time. How can we unlock the secrets of faster-than-light travel, or at the very least, create propulsion systems that make interstellar missions feasible within the time frames that are relevant to human civilization? One of the most promising avenues for overcoming these limitations lies in the realm of theoretical physics, where scientists have begun to explore ways to manipulate space-time itself. While it sounds like science fiction, one of the most discussed concepts in this area is the idea of a warp drive. The concept of the warp drive originates from the work of physicist Miguel Alcubierre, who proposed a method of faster-than-light travel based on the idea of a warp bubble. Essentially, the warp drive would not involve a spacecraft moving through space faster than light. Instead, it would involve contracting space in front of the spacecraft and expanding space behind it, creating a bubble of space-time that moves faster than light. This would theoretically allow a spacecraft to travel vast distances in a short amount of time without violating the laws of relativity, because the spacecraft itself is not moving faster than light through space. It is simply moving through a space that is being manipulated. The concept of the warp drive has captivated the imaginations of scientists and science fiction fans alike, but it remains firmly in the realm of theoretical physics. The major challenge is that creating a warp bubble requires a vast amount of negative energy, something that we currently do not have the ability to generate or manipulate. Even if we could, the energy requirements for such a system would be astronomical, far beyond anything humanity has ever achieved. Nevertheless, the idea of manipulating space-time opens up exciting possibilities for the future of interstellar travel, suggesting that the answer to the speed of light limitation may not lie in the propulsion of the spacecraft itself, but in the very fabric of space around it. But what if manipulating space-time is not a realistic possibility? What other options do we have for making interstellar travel feasible? One alternative lies in the concept of propulsion systems that can achieve a significant fraction of the speed of light, enough to make a journey to the nearest stars within a human lifetime. The idea of using nuclear propulsion is one such concept that has been explored in various forms. Nuclear propulsion offers several advantages over traditional chemical rockets, primarily in terms of fuel efficiency. A nuclear-powered spacecraft could, theoretically, carry far less fuel than a conventional rocket, and still achieve much higher speeds, allowing it to reach other stars in a matter of decades rather than centuries. One of the most ambitious proposals in the field of nuclear propulsion is the concept of nuclear fusion drives. Fusion, the process that powers the sun, involves combining lightweight atomic nuclei to release vast amounts of energy. A fusion-powered spacecraft would harness the same principles, using the energy produced by fusion reactions to generate thrust. This type of propulsion could provide a much more efficient means of traveling to the stars, potentially allowing a spacecraft to reach speeds close to 10% of the speed of light. While we have made some progress in the development of fusion reactors here on Earth, we are still far from achieving the level of control and efficiency required to use fusion for space propulsion. However, if we can overcome these technological hurdles, fusion propulsion could open the door to interstellar travel, allowing us to reach the stars in a matter of decades rather than millennia. Another concept worth exploring is the idea of using antimatter propulsion. Antimatter is the mirror image of regular matter. When antimatter and matter collide, they annihilate each other in a burst of energy. Theoretically, this could be harnessed to create extremely efficient propulsion systems. The energy released from the annihilation of even small amounts of antimatter is far greater than that produced by any other form of fuel. However, creating, storing, and using antimatter in quantities sufficient for interstellar travel present significant challenges. Currently, antimatter is produced in extremely small quantities in particle accelerators, and we have no reliable means of storing it. Moreover, the energy required to create antimatter far exceeds the energy that could be gained from its annihilation. Nonetheless, the concept of antimatter propulsion remains one of the most exciting theoretical possibilities for achieving faster-than-light travel. While nuclear propulsion and antimatter are certainly exciting concepts, another promising approach to interstellar travel involves harnessing the power of light itself. This brings us to the concept of solar sails, a technology that has already been demonstrated in space on a small scale. A solar sail is essentially a large, thin sail that is propelled by the pressure exerted by photons, the particles of light. Unlike traditional propulsion systems that rely on chemical reactions or nuclear power, solar sails take advantage of the fact that light, despite having no mass, carries momentum. When light strikes the sail, it transfers momentum, pushing the sail forward. While the acceleration generated by this method is small, over long distances and time periods, it can accumulate to substantial speeds. One of the most notable examples of solar sail technology is the Breakthrough Starshot initiative, which aims to send small, lightweight spacecraft to the Alpha Centauri system, the closest star system to our own, using powerful lasers to propel small sails. The idea behind Breakthrough Starshot is to build tiny spacecraft, each roughly the size of a postage stamp, equipped with a solar sail that would be propelled by high-powered lasers beamed from Earth. These spacecraft would be able to achieve speeds of up to 20% of the speed of light, making the journey to Alpha Centauri possible within a human lifetime. While the project is still in its early stages, it demonstrates that even without relying on traditional propulsion methods, we may one day be able to send probes to the stars at unprecedented speeds. Of course, achieving interstellar travel with any of these methods will require advances in technology that are still many years, if not decades away. But perhaps the most crucial piece of the puzzle is understanding the fundamental physics that govern space-time, propulsion, and energy. Until we unlock these mysteries, interstellar travel will remain an aspiration rather than a reality. The pursuit of faster-than-light travel, or at least travel at a significant fraction of the speed of light, is not just about reaching other stars. It is about fundamentally changing our relationship with the universe. The challenges we face are vast, but so are the rewards. The potential to reach other stars, to explore the unknown, and perhaps to discover new life, represents the next great leap for humanity. We may not know exactly how we will get there, but the journey driven by curiosity, innovation, and a desire to push beyond the boundaries of what we know has already begun. Whether through warp drives, fusion engines, antimatter propulsion, or solar sails, the dream of interstellar travel is alive, and it is within our grasp. As humanity continues to explore the vastness of space, we are confronted with a fundamental question: how do we sustain life during the long journeys to distant stars? The sheer distances involved in interstellar travel pose a set of unprecedented challenges that go beyond the scope of our current space exploration capabilities. To make this journey possible, we must innovate not only in propulsion systems, but also in the life support technologies that will enable humanity to survive and thrive in the cold, empty void of space for centuries at a time. Interstellar travel is not merely about sending probes or robots into the cosmos. It's about creating sustainable environments where humans can live, reproduce, and function across generations. The challenges of human survival in space go far beyond the technical aspects of spacecraft design. They are deeply intertwined with the biological and psychological needs of the astronauts who would undertake these journeys. One of the first and most critical issues that must be addressed is how to provide the basic necessities for life: food, water, and air. On Earth, these resources are abundant and readily available. However, in the confines of a spacecraft traveling through deep space, everything becomes much more difficult. The spacecraft must be a self-sustaining environment, capable of recycling and replenishing these resources over an extended period of time. This is where life support systems come into play. Traditional spacecraft, like those that have been used for missions to the International Space Station, ISS, rely on resupply missions to maintain adequate levels of food, water, and oxygen. However, this system is not viable for interstellar missions, which could last decades or centuries. The vast distances involved mean that resupply missions are impossible. Therefore, we must develop closed-loop life support systems that can recycle air, water, and waste in a way that supports human life indefinitely. These systems must be able to purify water, regenerate oxygen, and remove carbon dioxide and other waste products from the air. Technologies like water filtration, oxygen generation systems, and waste recycling will need to be perfected to ensure that astronauts can survive without the need for external supplies. One promising approach to this challenge is the concept of biogenerative life support systems. These systems mimic the processes that occur in Earth's biosphere, where plants and animals work together to maintain a stable, life-sustaining environment. In a biogenerative system, plants could play a key role by producing oxygen through photosynthesis, while also absorbing carbon dioxide and providing food. A carefully balanced ecosystem of plants, fungi, and microorganisms could be employed to create a closed-loop system where resources are constantly recycled. For instance, plants would not only produce oxygen but could also provide a sustainable source of food, using nutrients derived from waste products like carbon dioxide and water. This type of system would help reduce the need for human intervention, allowing astronauts to live more naturally in space and better mimic Earth's self-sustaining ecosystem. However, biogenerative systems are not without their challenges. Maintaining a healthy ecosystem in a sealed environment is a delicate balance, and even small changes in temperature, humidity, or light levels can disrupt the system. The physical limitations of spacecraft will also pose a problem. Growing enough food to sustain a crew on a long-term mission to another star will require significant space, light, and energy. One solution may be to design spacecraft with large, dedicated agricultural areas, where crops could be grown in controlled environments. Advances in hydroponics, aeroponics, and vertical farming may make this a viable option. These techniques use little water, require less space, and allow for high-density farming, all of which are critical when considering the limited space available in a spacecraft. Aside from the biological challenges of growing food and recycling resources, one of the most pressing concerns for interstellar travel is the psychological well-being of the astronauts. The journey to another star could take decades or even centuries, and astronauts would be isolated from Earth for long periods. Prolonged isolation in the confined space of a spacecraft, with limited social interaction, could have profound psychological effects. Astronauts may experience a range of issues including depression, anxiety, and sleep disturbances, all of which could impair their ability to function effectively. Even today, astronauts aboard the ISS experience the effects of isolation and confinement, and the mental toll of these conditions is one of the primary concerns for long-duration space missions. To address these challenges, interstellar missions will need to incorporate advanced psychological support systems. These systems must not only monitor the mental health of the crew, but also provide mechanisms for reducing stress and maintaining a sense of normalcy. Social isolation is one of the greatest dangers in long-duration space missions, and it could be exacerbated by the complete disconnect from Earth. As such, the design of interstellar spacecraft must include opportunities for social interaction, recreation, and mental stimulation. This could take the form of communal spaces where the crew can relax and bond, as well as access to entertainment, virtual reality experiences, and communication systems that allow them to stay in touch with loved ones and the rest of humanity. In addition to these immediate concerns, we must also consider the long-term implications of living in space. The effects of weightlessness or microgravity on the human body are well documented. Prolonged exposure to microgravity causes muscle atrophy, bone loss, and changes in the cardiovascular system. On Earth, our bodies are adapted to the constant pull of gravity, which helps maintain bone density and muscle strength. In space, the lack of gravity means that bones and muscles are not being used to their full potential, leading to a gradual deterioration. To counteract these effects, astronauts aboard long-duration missions must engage in regular exercise to maintain their physical health. However, even with exercise, the body still undergoes significant changes in microgravity, and the long-term consequences of these changes are still largely unknown. One of the more surprising effects of prolonged space travel is the impact on the immune system. Studies have shown that exposure to the microgravity environment of space can impair the immune system, making astronauts more susceptible to infections. In the confined space of a spacecraft, this is a particularly worrying issue. Ensuring the health and safety of the crew will require careful monitoring of their immune systems, as well as strategies to protect them from potential infection. The design of spacecraft and interstellar habitats must also take into account the need for sterile environments to prevent the spread of pathogens. Moreover, deep space is filled with radiation from cosmic rays and solar particles that can pose a significant threat to human health. Beyond the protective shield of Earth's atmosphere and magnetic field, astronauts will be exposed to high levels of radiation. Cosmic radiation is particularly dangerous because it is highly energetic and can penetrate spacecraft shielding. Chronic exposure to this radiation could lead to an increased risk of cancer, genetic mutations, and other health problems. To mitigate this risk, spacecraft and habitats must be designed with radiation protection in mind. This might involve thick layers of shielding, or possibly even using the spacecraft's own water or other resources as a protective barrier. Another potential solution is the development of electromagnetic shielding, which could generate a magnetic field to deflect charged particles from space. In addition to radiation, there are other environmental factors that must be addressed. Space is an unforgiving environment. Extreme temperatures, lack of atmosphere, and the vacuum of space present constant threats. The spacecraft will need to be equipped with sophisticated thermal control systems to regulate temperature and maintain the comfort and safety of the crew. These systems will need to operate seamlessly for decades, requiring an unprecedented level of reliability and redundancy. Another crucial issue is the long-term psychological impact of space travel, particularly as it pertains to future generations. If humanity embarks on interstellar missions involving generational ships, the crew will likely experience profound changes in how they view their identity and their place in the universe. For generations born aboard a spacecraft, Earth may seem like a distant, abstract concept. They may lose the connection to the planet that gave them life, and their culture and language may evolve independently from Earth-based humanity. This sense of isolation and disconnection could result in psychological challenges that are distinct from those faced by their ancestors. In the end, sustaining life on interstellar journeys requires more than just overcoming the technical and biological challenges. It requires an understanding of how humans adapt to living in space, and how we can create environments that support physical, psychological, and emotional well-being. Whether through bioregenerative systems, cutting-edge medical technologies, or innovative designs for social interaction and community building, the future of interstellar travel hinges on our ability to replicate and sustain the conditions that make life possible on Earth. With the right technologies, resources, and approaches, humanity can one day embark on the long journey to the stars, facing the challenges of space not just as explorers, but as the next step in the evolution of life itself. As humanity stands on the precipice of the greatest leap in our history, interstellar exploration, a crucial question looms large. How do we ensure that we not only survive in the depths of space, but also thrive? The challenges of traveling beyond our solar system are vast, from the terrifying emptiness of interstellar space to the immense technological and physiological obstacles. However, one of the most compelling aspects of interstellar exploration is the potential for innovation. For every problem that arises, there exists the possibility of finding a solution that radically alters the way we live, think, and interact with the cosmos. This journey to the stars is not just about traveling farther, it's about reinventing what it means to be human, creating new technologies, and discovering untold opportunities for the future of our species. At the heart of this process of reinvention lies the concept of sustainable energy generation, the energy required to propel a spacecraft to another star, while maintaining life support systems, recycling resources, and overcoming the challenges of deep space, is incomprehensibly vast. This means that developing sustainable and scalable energy generation methods is not just a convenience, It's an absolute necessity for the success of any interstellar mission. But how do we generate the required energy when the solar panels that power modern spacecraft would be rendered ineffective long before we leave the reach of our sun's rays? How do we ensure that we have enough power to sustain life and complete the journey, whether it's through fusion reactors, antimatter, or even harnessing the very forces of space itself? One of the most promising solutions to the energy problem is nuclear fusion. Fusion, the process that powers the stars, has the potential to provide an almost limitless amount of energy. It involves fusing lightweight atomic nuclei, typically isotopes of hydrogen like deuterium and tritium, to form helium, releasing enormous amounts of energy in the process. Unlike nuclear fission, which splits atoms and produces hazardous waste, fusion generates energy without the dangerous byproducts. The sun itself is a fusion reactor, and its energy output sustains life on Earth. If humanity can replicate this process in a controlled manner, it could provide an incredibly efficient and sustainable energy source for interstellar missions. While nuclear fusion holds great promise, harnessing it for spacecraft propulsion presents significant challenges. We have yet to create a fusion reactor that operates continuously at a net positive energy output, i.e. a reactor that produces more energy than it consumes. Numerous international projects, such as the ITER International Thermonuclear Experimental Reactor in France, are working toward achieving controlled nuclear fusion. However, despite decades of research, we remain far from a commercial functional fusion reactor. Yet, the very fact that humanity is working toward this energy breakthrough points to the transformative potential it holds. If fusion power can be realized, it could be used to propel spacecraft to speeds unimaginable today, drastically reducing travel times to distant stars and providing the energy necessary for all other systems aboard the spacecraft. In the meantime, other energy sources are also being explored. One of the more speculative yet fascinating ideas is the use of antimatter as a power source. Antimatter, essentially the opposite of matter, is made up of antiparticles. When antimatter comes into contact with regular matter, they annihilate each other in a release of energy so powerful it surpasses any conventional energy source. Theoretically, antimatter could provide the highest energy yield per unit of mass, making it ideal for interstellar propulsion. However, antimatter is not something that we can easily manufacture or store in sufficient quantities. Currently, the production of antimatter requires enormous amounts of energy, far more than the energy we could ever hope to extract from it. Creating a stable and efficient antimatter propulsion system remains one of the most daunting challenges in space exploration. Yet, despite the technical difficulties, antimatter propulsion holds the potential to revolutionize space travel if the barriers can be overcome. Beyond harnessing traditional or theoretical energy sources, another avenue for interstellar propulsion lies in the concept of solar sails. Solar sails rely on the pressure exerted by light, or more specifically photons, on a reflective surface to generate propulsion. While the amount of thrust generated by a single photon is minuscule, the concept behind solar sails is that over vast distances and long periods, the cumulative effect of photons pushing against the sail could accelerate a spacecraft to significant speeds. Solar sails have already been demonstrated in space by missions such as the Planetary Society's LightSail and Japan's Icaros spacecraft. But scaling this technology for interstellar travel will require much larger and more powerful sails. Enter the Breakthrough Starshot initiative. This bold project aims to send small, lightweight probes to the Alpha Centauri star system, located just over 4 light-years away. These probes would be equipped with solar sails that would be propelled by powerful ground-based lasers. If successful, these probes could achieve speeds of up to 15 to 20% of the speed of light, making a journey to Alpha Centauri in just a few decades. A far cry from the thousands of years it would take with conventional propulsion methods. Breakthrough Starshot's technological challenges are immense, but the project represents the first serious attempt at interstellar exploration, and the results could fundamentally change our understanding of how we travel across the cosmos. Yet even with breakthrough propulsion methods like solar sails, fusion, or antimatter, we must also consider the fundamental constraints imposed by the nature of space itself. As we venture deeper into the galaxy, we are confronted with not only the challenge of traveling across vast distances, but also the harsh and unpredictable environment of deep space. Space is filled with cosmic radiation, dust, and other hazards that could pose a grave threat to both crew and spacecraft. This radiation, which comes from distant stars, supernovae, and other cosmic phenomena, is not only harmful to human health, but could also damage sensitive electronics aboard the spacecraft. It is one of the greatest threats to the long-term survival of interstellar missions. To mitigate this risk, spacecraft will need to be equipped with advanced shielding technologies capable of protecting them from radiation. This could include traditional methods, such as thick walls of lead or other heavy materials, but these would add significant weight to the spacecraft. Alternatively, scientists are exploring more innovative solutions, such as electromagnetic shielding, which could deflect charged particles and cosmic rays using magnetic fields. This technology would be analogous to the Earth's magnetic field, which protects us from the harmful effects of solar radiation. Though still theoretical, the development of electromagnetic shielding could be a game changer, offering an effective way to shield spacecraft from the hazards of deep space. In addition to radiation, another challenge for interstellar travel is the problem of time itself. A journey to the stars, especially if it involves human crews, is not just about traveling long distances, but also about managing the passage of time. A trip to even the nearest star systems would span generations, meaning that a single mission could last hundreds of years. For such a long journey, we need to consider not only how to keep the crew alive and healthy, but also how to ensure the sustainability of the mission over generations. This brings us to the concept of generational ships. A generational ship is a spacecraft designed to carry not just astronauts but entire communities of people, families, workers, and specialists. Across interstellar distances, these ships would be self-sustaining, with ecosystems that generate food, water, and oxygen, and with systems to recycle waste. Over the course of the journey, multiple generations would be born, live, and die aboard the ship. Such missions would require an entirely new approach to governance, education, and social systems, as the crew would likely never see Earth again. The psychological and sociological impacts of life on a generational ship would be profound, and ensuring the success of such missions would depend on creating systems that promote social cohesion and mental well-being over extended periods of isolation. In addition to generational ships, we must also consider the potential for cryogenic sleep, or hibernation, to make interstellar travel more feasible. The idea is to freeze or hibernate astronauts during the journey so that they do not age during the long trip. This would eliminate the need for large crews on generational ships, and could make it possible for a small crew to operate the spacecraft, while the majority of the passengers remain in suspended animation. The technology to safely preserve human life in such a state, and then revive astronauts without causing harm, is still in its infancy, but the potential for cryogenics to revolutionize space travel is immense. Whether it's through revolutionary propulsion technologies, sustainable life support systems, or the creation of self-sustaining ecosystems, the journey to the stars requires the development of groundbreaking innovations that will fundamentally alter the way we live and work. These technologies will not only make interstellar travel possible, but will also have profound implications for life here on Earth. The drive to explore the cosmos will push us to create new technologies, to challenge the very limits of what we thought was possible, and to inspire future generations to continue the quest for knowledge, discovery, and the survival of humanity. The journey ahead is long, but it is a journey that we must undertake not just for the future of space exploration, but for the future of life itself. As humanity begins to explore the possibility of interstellar travel, one of the most profound challenges lies not only in reaching the stars, but also in ensuring that we can thrive once we arrive. The idea of leaving our solar system behind to explore distant star systems is exhilarating, yet it requires us to rethink many aspects of what it means to be human, how we interact with space, and how we create self-sustaining systems that allow us to live and prosper in environments completely different from Earth. The leap from interplanetary to interstellar travel isn't just a matter of scaling up technology, it's about creating entirely new approaches to propulsion, life support, energy generation, and long-term survival in space. But perhaps the most fundamental question remains: when we do finally reach a distant star system, what then? What challenges will we face in terms of colonization, and how can we ensure that humanity's expansion into the stars is not only possible but sustainable and ethical? The concept of interstellar colonization has long been a fixture of science fiction. For years, we've envisioned humanity establishing colonies on planets orbiting distant stars, much like we once dreamed of settling the Moon or Mars. But interstellar colonization is far more complex than just planting flags and building cities on new worlds. It's not simply about technological prowess or engineering feats. It's about creating societies that can endure in environments where every aspect of life must be carefully managed. There are a multitude of factors to consider, ranging from the physical and psychological health of the colonists to the sustainability of the ecosystem they will depend on. And beyond the technical and logistical issues, there are profound ethical considerations. Who gets to decide which planets are colonized, and who is responsible for ensuring the protection of any existing life, indigenous or otherwise? As we embark on the quest for distant worlds, the first step will be to identify planets that are capable of supporting human life. The search for exoplanets has already yielded some promising candidates, planets in the habitable zone of their stars, where conditions are right for liquid water to exist. Proxima Centauri b, a planet orbiting our closest star, Proxima Centauri, has generated significant interest in this regard. With a size similar to Earth and located in its star's habitable zone, Proxima b could potentially support life. However, while such planets are exciting prospects, there are many factors that make them far from ideal for human habitation. One major issue is the radiation environment around most stars, particularly those that are smaller and cooler than our Sun. Stars like Proxima Centauri are prone to frequent solar flares and high levels of radiation that could pose a significant threat to any potential human settlers. In fact, the high levels of radiation on Proxima Centauri b could make it a dangerous environment for human life without significant technological intervention. Even with the best shielding, the constant bombardment of radiation could result in severe health risks for the colonists. Therefore, before establishing any colonies, we would need to develop highly advanced protection systems, perhaps electromagnetic fields or advanced materials that can block harmful radiation. This would also necessitate the development of habitats that are able to provide full protection for the colonists, ensuring that they can live in relative safety. Another challenge of interstellar colonization is the need for self-sustaining ecosystems. On Earth, ecosystems are incredibly complex, with each element, air, water, soil, plants, and animals, playing a critical role in sustaining life. Recreating such systems on a distant planet is no easy feat, especially given that the conditions of each planet will vary. To support human life in a sustainable way, we would need to create a biosphere capable of maintaining oxygen levels, providing food, recycling water, and handling waste. Bioregenerative life support systems, which mimic the natural processes of Earth's ecosystems, will play a key role in this. These systems could include plants that generate oxygen through photosynthesis, animals or insects that help control pests and create waste that can be recycled into food for the plants, and microorganisms that break down waste and provide the nutrients needed for crops to grow. The challenge will be to create a balanced, self-sustaining environment where every element interacts to maintain equilibrium, much like Earth's natural systems. This will also require the development of closed-loop systems that recycle air, water, and food indefinitely. Currently, technologies like hydroponics and aeroponics, which allow plants to grow without soil, are being developed and tested for use in space. These systems could be integral to maintaining sustainable agriculture in space colonies. However, there are still many challenges to overcome, namely, ensuring that these systems are able to handle the scale of interstellar colonization. Unlike the small-scale experiments we've seen on the International Space Station, interstellar colonies will require entire ecosystems that can support hundreds or even thousands of people for extended periods of time. This necessitates both reliable technology and careful planning, as the survival of the colony will depend on the successful interaction of these systems. Then there is the question of the human psyche. Spending extended periods in space is known to have profound effects on human health, not just physically, but also psychologically. Astronauts on the International Space Station often experience feelings of isolation, confinement, and stress. These psychological effects are compounded by the lack of normal day-night cycles, limited space, and a sense of disconnection from Earth. For interstellar missions, which could last for generations, the psychological toll could be even more significant. Colonists may never return to Earth, and their descendants may have no direct connection to the home planet. The isolation and sense of detachment could have serious consequences on their mental health and social dynamics. To address this, the design of interstellar habitats will need to include spaces for recreation, exercise, and social interaction. Artificial environments could mimic Earth's landscapes and provide psychological comfort for the colonists. Furthermore, keeping the colonists mentally and emotionally engaged will be essential for long-term mission success. This could include access to virtual reality systems, entertainment and communication systems, that allow the colonists to stay in contact with Earth, at least initially. However, even these measures might not fully mitigate the stress and challenges of living in a completely enclosed environment for decades or centuries. Beyond these technical and psychological challenges, we must also consider the ethical implications of colonization itself. In the past, human colonization has been a contentious issue, often resulting in exploitation, the destruction of ecosystems, and the displacement of indigenous populations. As we look to the stars, we must ask ourselves how we can avoid repeating these mistakes. Should we colonize planets even if they have ecosystems or life forms, even if we cannot immediately recognize them as intelligent? If we find life on another planet, whether microbial or more advanced, do we have the right to alter their environment for our own benefit? These are difficult questions, and as we venture into space, we must ensure that our expansion into the stars is done with respect and responsibility. The ethical considerations of interstellar colonization extend to issues of resource allocation. If humanity begins colonizing other planets, the resources required to do so, energy, materials, labor, will be immense. Who gets to decide how these resources are distributed? Who will be the colonists, and how will they be chosen? Will we create a new form of spacefaring elite, or will interstellar missions be an endeavor that is accessible to all? These are complex social issues that will need to be addressed in the planning of future space missions. Ensuring that space exploration is conducted fairly and equitably will be crucial to the success of these efforts. Finally, as we begin to colonize other worlds, we must also recognize that the very act of colonization will change humanity itself. Generations born on distant planets will experience a vastly different life than those on Earth. They will not only grow up in environments shaped by artificial systems, but may also adapt to new environments in ways that we can't yet predict. The long-term impacts of living in space, whether in microgravity or on planets with different atmospheric conditions, could lead to significant physiological changes in the human body. Over time, colonists may evolve in ways that make them distinct from their Earth-based ancestors. This could raise questions about identity and belonging. Will these colonists still consider themselves Earthlings, or will they develop their own unique cultural, social, and biological identity? The potential for divergence over many generations could lead to new forms of human civilization, perhaps even creating a truly interstellar species. In the end, the dream of interstellar colonization is both a technical challenge and a moral responsibility. It represents the greatest ambition of our species to reach out to the stars, to find new worlds, and to ensure that humanity's future is not limited to a single planet. However, this pursuit must be tempered with caution and respect for the unknown. As we journey to the stars, we must consider not only the technological solutions, but also the ethical, social, and environmental implications of such a monumental undertaking. The legacy of interstellar colonization will be defined not just by our ability to reach other worlds, but by the values we carry with us, and the ways in which we choose to shape the future of humanity in the cosmos. As humanity sets its sights on the stars, one question looms larger than any other. What does the future hold for our species in the vastness of space? The quest for interstellar travel and colonization is not merely about reaching distant planets or moons. It's about understanding our place in the universe, pushing the boundaries of human potential, and ensuring the survival of life on Earth and beyond. As we contemplate the challenges ahead, propulsion systems, life support, resource management, and ethical dilemmas, we must also think about the long-term future of humanity and what kind of civilization we hope to build in the stars. In the far future, the ability to travel between stars will not just be the result of technological innovation, it will be a fundamental shift in how we perceive ourselves as a species. Today we live on a single planet, bound by gravity and confined to a solar system. Yet, as we venture out into the galaxy, we will begin to transcend these constraints, becoming a spacefaring civilization capable of spreading life to distant worlds. But this transformation will not happen overnight, nor will it come without significant challenges. It will require a fundamental shift in our understanding of time, resources, and the very nature of human existence. The concept of a Type II civilization on the Kardashev scale, which measures the technological advancement of a civilization based on its energy consumption, provides a useful framework for understanding humanity's potential future in space. A Type I civilization harnesses the energy of its home planet, while a Type II civilization is capable of harnessing the energy of an entire star. This would mean building massive structures like Dyson spheres, artificial constructs that surround a star and capture its energy. Such a civilization would be able to colonize entire star systems, harvesting energy from multiple stars and utilizing it to power interstellar travel, terraforming planets, and sustaining large-scale space infrastructure. At this level of advancement, humanity would not just be a single species living on Earth. We would be a multi-planetary species, spreading across the galaxy and establishing colonies on worlds that were once thought to be beyond reach. We would have the technology to manipulate entire ecosystems, terraform planets to make them habitable, and build massive space stations that serve as hubs for interstellar trade and exploration. The technologies required to achieve this type of civilization, fusion energy, artificial gravity, matter energy conversion, and interstellar propulsion, are still far from being realized, but they represent the direction in which we are heading. One of the most exciting possibilities for humanity's future is the concept of genetic adaptation and evolution in space. As we venture further from Earth and establish colonies on distant worlds, the environments of these planets will be vastly different from what we know. The gravity on these planets may be stronger or weaker, the atmospheric conditions could be radically altered, and the levels of radiation may be far higher than what we experience on Earth. To survive and thrive in these new environments, humans will likely need to adapt biologically, perhaps through genetic modification, selective breeding, or even cybernetic enhancements. Genetic modification is already being used on Earth to cure diseases and enhance the human body's capabilities. But in the future, it could play a central role in helping us survive in space. For example, astronauts who spend long periods in microgravity suffer from muscle atrophy and bone density loss. Genetic modifications could help make our bones and muscles stronger and more resilient to the effects of space. Similarly, colonists on planets with low gravity might need genetic enhancements to ensure they maintain muscle and bone density. On planets with higher levels of radiation, humans may need to develop more robust DNA repair mechanisms to prevent the harmful effects of cosmic rays. These genetic modifications, coupled with cybernetic enhancements, could allow humanity to adapt to environments that were once considered inhospitable, opening up new frontiers for human colonization across the galaxy. Moreover, as interstellar travel becomes a reality, humanity will likely face the challenge of long-term space missions that span generations. A single journey to a distant star could take hundreds, if not thousands of years. For such missions to succeed, we will need to find ways to preserve human life over multiple generations. This could involve the development of advanced cryogenic technologies, allowing people to be put into suspended animation for the duration of the journey, or the creation of closed-loop ecosystems capable of supporting life indefinitely. The concept of generational ships, where entire communities live and die aboard spacecraft, has already been explored in science fiction, but it is increasingly looking like a feasible option for humanity's long-term survival in space. Generational ships, however, would present a host of social, psychological, and political challenges. The people who board such ships would be part of a multi-generational mission, and their descendants would be the ones to reach the destination. This raises profound questions about identity, governance, and culture. Would the people born on these ships consider themselves to be Earthlings, or would they develop a distinct identity separate from the planet they came from? How would power be distributed aboard these ships? Who would make the decisions about where and when to colonize new planets? These are not questions we can answer easily, but they are questions that we must begin to consider as we prepare for humanity's future beyond Earth. One of the most intriguing possibilities for the future of humanity in space involves the concept of digital immortality. If we are able to map the human brain in its entirety, we may one day be able to upload consciousness into machines. This could allow us to preserve the essence of who we are, our thoughts, memories, and personalities, long after our physical bodies have aged or died. Digital immortality could revolutionize space exploration, as it would allow humans to travel to distant stars without the need for biological preservation. A digital consciousness could be transmitted across the stars, bypassing the constraints of time and space. However, this raises a number of ethical and philosophical questions. If a person's consciousness is uploaded into a machine, does that still make them human? What happens to the person's identity, their soul, or their sense of self? These are questions that will likely need to be addressed as the technology for digital immortality progresses, and they will shape the future of humanity's role in the universe. As we look further into the future, We also have to consider the environmental impact of our expansion into space. Just as humanity's growth on Earth has been accompanied by significant ecological changes, our expansion into the galaxy will have profound consequences for the environments we encounter. The process of terraforming planets to make them habitable, for example, will require massive amounts of energy and resources. How will we ensure that we do not repeat the mistakes of Earth's past, where unchecked industrial growth led to environmental degradation? As we venture into space, we must also develop sustainable practices to preserve the natural ecosystems of the planets we colonize. This could involve creating closed-loop systems that recycle resources efficiently, minimizing waste, and ensuring that new ecosystems are able to thrive without being destroyed by human interference. Humanity's future in space, however, is not just about technological innovation, colonization, or genetic adaptation. It's about understanding our role in the broader cosmos and our relationship to the universe. What is our purpose in this vast, unfathomable expanse of stars and galaxies? As we explore and colonize distant planets, we must also consider the deeper philosophical and spiritual questions that arise. Are we merely explorers, or is there a greater destiny for humanity in the stars? What responsibilities do we have, not only to each other and to future generations, but also to the potential life forms we may encounter along the way? One of the most profound realizations of interstellar exploration is the realization of just how small and fragile we are in the grand scale of the universe. As we reach for the stars, we will inevitably confront the vastness of time and space, and in doing so, we will be forced to confront the existential questions that have always haunted humanity. Why are we here? What is the meaning of our existence? What is our place in the universe? These questions may never have definitive answers, but the journey toward the stars is in itself an attempt to find meaning in the vastness of space. In the end, the future of humanity in space is not just about technological prowess or colonizing new worlds. It's about pushing the boundaries of what it means to be human. It's about embracing our potential as a species, evolving beyond the limits of our biology, and expanding our reach across the galaxy. As we venture into the unknown, we will continue to ask difficult questions and face profound challenges, but we will also discover new opportunities, new forms of life, and perhaps even new ways of understanding the universe and our place in it. The journey is long, and the path ahead is uncertain, but the potential for discovery and growth is limitless. The future of humanity in space is a future of endless possibilities, and it is a future we are only just beginning to explore. As we continue to look toward the stars, one of the most significant and compelling aspects of interstellar exploration is the question of how we will maintain and preserve human life across the immense distances of space. While technological advancements in propulsion, life support, and energy generation will certainly play a central role in making interstellar travel possible, there is another vital consideration. How will we ensure that we can successfully navigate the challenges of time, isolation, and the profound psychological and social changes that will come with the colonization of distant star systems? The journey to the stars will take time, not just years, but centuries and potentially millennia. As we venture into space, we will need to ensure that we are not just capable of surviving, but that we can also build thriving, self-sustaining, and flourishing communities that will adapt to the unique challenges of interstellar life. One of the first and most critical considerations for interstellar travel is the preservation of life over the long, grueling journey. When we think of space travel, we often picture astronauts aboard the International Space Station, or small crews on short-term missions to the Moon or Mars. These missions are relatively brief, with astronauts returning to Earth after months or years. Interstellar missions, on the other hand, will last much longer, perhaps hundreds or thousands of years. Given these timescales, it will be impossible for a single generation of astronauts to complete the journey, which means that the mission must continue through multiple generations. This creates a fundamental challenge for interstellar exploration. How do we ensure that humanity can not only survive, but thrive for such a long period of time in the isolated confines of a spacecraft or on a distant planet? The concept of generational ships, spacecraft that carry multiple generations of humans on their journey through the stars, presents one possible solution. A generational ship would be a self-sustaining environment where humans could live, reproduce, and pass on knowledge over the course of a long journey to a distant star. The key to making this type of interstellar mission viable is the creation of closed-loop ecosystems that can support human life indefinitely. These systems would need to be capable of recycling air, water, and nutrients, as well as producing food for the crew. The environment aboard the spacecraft would have to function as a miniature version of Earth's biosphere, maintaining the delicate balance between plants, animals, and microorganisms that allows life to thrive. The biological aspect of sustaining life on a generational ship is certainly challenging, but it is not the only hurdle we must overcome. The psychological and social dynamics of living aboard a spacecraft for generations would be equally complex. For the people aboard such a ship, life would be defined by isolation, confinement, and a lack of connection to the world they left behind. They would be born, live, and die on the ship, with little to no contact with Earth or any other human civilization. Even with advanced technology that might allow for virtual communication with Earth, the sense of detachment from the home planet could be overwhelming. The crew would not just be astronauts, they would be the ancestors of future generations, with the hopes and dreams of an entire civilization resting on their shoulders. To maintain mental and emotional well-being, the design of a generational ship would need to consider how to combat feelings of isolation and confinement. Social and psychological support would be critical for ensuring that the mission is successful. Crew members would need access to recreational spaces, opportunities for personal expression, and social interactions that foster a sense of community. Education would also be a crucial component. Children born on a generational ship would need to be educated in a way that prepares them not only for life aboard the ship, but for the eventual settlement of new worlds. This education would need to be dynamic and adaptable, allowing for the development of new skills and knowledge as the mission progresses. The ship's inhabitants would need to pass down not only the practical knowledge of how to operate the ship and sustain life, but also the values and culture of humanity. Moreover, the leadership and governance structures aboard a generational ship would need to be carefully considered. In a small, closed environment, power dynamics can quickly become distorted. Ensuring that the leadership structure is fair, transparent, and accountable would be essential for maintaining social cohesion. Over the course of many generations, the original goals of the mission could become distorted or forgotten, so it would be important to preserve a sense of purpose and unity. It would also be crucial to create mechanisms for conflict resolution, as tensions and disagreements are inevitable in any close-knit society. The ability to adapt and innovate in response to unforeseen challenges would be key to the success of a generational mission. A major challenge with generational ships, however, is that they are not a perfect solution. The ability to sustain life for generations aboard a spacecraft presents numerous technical difficulties, particularly with respect to maintaining a balance between energy usage, resource management, and human health. The systems aboard a generational ship would need to be incredibly robust and resilient, as any failure in a critical system such as life support, food production, or waste recycling could have catastrophic consequences. The risk of disease or pest infestations could also jeopardize the ship's ecosystem, and ensuring the long-term health of the crew would be a constant concern. Additionally, the psychological burden of living in such an environment could take a toll on the mental health of the crew, especially over generations. An alternative approach to generational ships is the concept of cryogenic sleep, or hibernation, in which astronauts are put into a state of suspended animation for the duration of their journey. This would eliminate the need for large, self-sustaining ecosystems and drastically reduce the logistical challenges of long-term space missions. The idea of using cryogenic technology to preserve human life for extended periods is still in its infancy, but it holds significant promise. Cryogenic sleep could allow astronauts to sleep through the journey, emerging only when they arrive at their destination. This would not only alleviate the psychological and social challenges of long-term space travel, but also prevent the physical degradation of the body that occurs in microgravity. However, cryogenic sleep also presents significant challenges of its own. The technology to safely preserve and revive human bodies is not yet available, and there are concerns about the potential damage to cells, tissues, and organs during the freezing and thawing process. There are also unknowns about the long-term effects of being in a suspended state. For instance, how would the human body respond to reanimation after being in cryogenic sleep for decades or centuries? While cryonics, the practice of freezing bodies for future revival, is a concept that has garnered interest in recent years, it remains highly speculative and experimental. Cryogenic technology would need to undergo significant advancements before it could be used to support interstellar missions. Another, more radical possibility for ensuring human survival on interstellar journeys is the concept of uploading consciousness into digital form. This idea, often referred to as mind uploading or digital immortality, proposes that it may one day be possible to scan and replicate a person's consciousness, effectively transferring it from the brain to a computer. If this were possible, astronauts could travel across the stars as digital entities, bypassing the constraints of biological life altogether. This would allow humans to live in space indefinitely, experiencing the journey and the destination in a virtual or simulated form. Mind uploading, however, raises a host of complex ethical and philosophical questions. If we upload a person's consciousness into a machine, does that person cease to exist? What happens to the soul if one believes in such a thing? How do we preserve the human experience if it's digitized and disconnected from the body? These are questions that, while speculative, will need to be addressed as we explore the potential for digital immortality. Despite these uncertainties, the idea of uploading consciousness has the potential to fundamentally change the nature of space travel, offering a new way for humanity to survive long-duration missions without relying on biological life. As we look toward the future of interstellar travel, it's clear that we are at the cusp of a new era in human history. The challenges of sustaining life across the vast distances of space are immense, but the opportunities for growth, discovery, and innovation are equally vast. Whether through generational ships, cryogenic sleep, or digital consciousness, humanity will need to be adaptable, resourceful, and resilient in the face of these challenges. The future of human space exploration will depend not only on our technological advancements, but also on our ability to create thriving, sustainable, and cohesive societies that can endure the hardships of life in space. Ultimately, the journey to the stars is not just about reaching new frontiers, it's about ensuring that humanity can thrive in those frontiers for generations to come. As we consider the possibility of interstellar travel, it becomes increasingly apparent that the journey we embark upon will not just be an extraordinary technological and physical challenge, but a profound psychological, social, and ethical endeavor. The very nature of interstellar travel, traveling across vast empty stretches of space that could take centuries or even millennia, presents a host of unique issues that humanity has never faced before. The future of interstellar exploration hinges on more than just propulsion systems and life support technologies. It also depends on how we build the social structures, cultural norms, and psychological resilience needed for such an ambitious undertaking. Our understanding of human psychology, social systems, and even ethics will need to evolve in ways we can hardly imagine today. The exploration and colonization of other star systems is not just about our capacity to survive physically, it's about ensuring the psychological and cultural continuity of humanity as we move beyond Earth. One of the most pressing issues in interstellar exploration is the long-term psychological impact of extended isolation. When astronauts venture into space today, even on missions to the International Space Station, they remain in regular contact with Earth. They have access to communication channels that allow them to maintain relationships with loved ones, receive updates from home, and stay connected to the world they left behind. For interstellar missions, especially those that span generations, the story will be vastly different. Communications with Earth will become increasingly limited as spacecraft travel further from our planet. Even with the most advanced communication technologies, the time delay in sending messages will be staggering, potentially hours, days, or even years between messages. The social isolation of interstellar travelers, combined with the psychological toll of being in a confined artificial environment for an extended period, could have profound effects. The journey will likely be carried out by multiple generations of humans, with descendants of the original crew being born, raised, and perhaps dying aboard the spacecraft. The psychological challenges here are immense. So over the course of such a journey, crew members may face profound loneliness and a deep sense of disconnection from their ancestral home. The sense of being cut off from Earth could lead to depression, anxiety, and social tension. Even with advanced virtual communication systems or regular communication with Earth, the inability to interact face-to-face with loved ones or experience the physical world outside the spacecraft would be a significant psychological burden. To address these challenges, we must look to the development of new strategies for supporting mental health during long-term space missions. One promising solution is the creation of virtual environments that simulate Earth-like conditions, providing astronauts with a psychological escape from the confines of the spacecraft. Imagine virtual reality systems that allow travelers to experience landscapes, places, or even entire worlds that mirror the Earth they left behind. Virtual parks, forests, oceans, and cities could serve as a form of psychological respite for those who are living in a sterile, artificial environment for generations. These virtual environments could offer more than just visual and auditory stimulation. They could simulate natural elements like wind, water, and sunlight, providing astronauts with sensory experiences that help maintain their mental and emotional well-being. However, even with virtual environments and communication systems, isolation will still be a significant challenge. It's not just about missing home or being far from Earth. It's about the fundamental human need for social connection and a sense of community. One of the central aspects of any long-term space mission, especially generational missions, will be the creation of resilient social structures. Astronauts on interstellar missions won't simply be a group of individuals working together for a limited time. They will be a society in their own right, with their own norms, values, and cultures. Over the course of a long journey, these societies will likely evolve in unexpected ways. The social dynamics aboard generational ships or in colonies on distant planets will need to adapt to the challenges of isolation, confinement, and an ever-changing environment. Ensuring social cohesion and harmony aboard an interstellar mission will require carefully designed governance systems that promote fairness, cooperation, and mutual support. If humanity is to thrive in space for generations, we must create systems that allow for effective decision-making, conflict resolution, and the maintenance of order. This may include democratic governance models that allow crew members to have a say in the direction of the mission and the establishment of laws that govern behavior aboard the spacecraft. The psychological effects of isolation and the unique challenges of living in a confined space for generations will require a delicate balance between individual autonomy and the collective good. Leadership will need to be flexible, transparent, and adaptable, ensuring that decisions reflect the needs of the mission and the well-being of the entire crew. Another key element of interstellar missions will be the preservation and transmission of knowledge across generations. The people aboard the spacecraft may not be the ones who reach the final destination. Instead, their descendants will be the ones to establish the first colony on a distant planet. As a result, the continuity of knowledge and culture will be crucial. This is not just about passing on technical knowledge related to the spacecraft's operations or survival systems. It's about maintaining the social, cultural, and ethical values that make us human. In the absence of direct contact with Earth, future generations will need to carry forward the lessons learned from their ancestors and preserve the identity of humanity. The transmission of knowledge across generations aboard a spacecraft will likely involve a combination of traditional education, technology, and memory systems. For instance, virtual reality simulations and advanced learning technologies could help ensure that each generation is able to learn the skills needed to operate the spacecraft and sustain the mission. At the same time, cultural education, passing on the stories, history, and values of humanity, will also play an important role. Digital archives, holographic storytelling, and virtual tutors could be used to preserve and communicate the experiences, struggles, and triumphs of previous generations. This process of cultural preservation will help ensure that the people of the spacecraft remain connected to their earthly roots and maintain a shared sense of purpose and identity as they journey through space. As we look toward the future, the ethical dimensions of interstellar travel will become even more pressing. If humanity is to become a spacefaring civilization, we will need to address not only the technical challenges of space travel, but also the moral implications of colonizing other worlds. The prospect of terraforming distant planets or moons to make them habitable for humans raises a host of questions about the ethics of interfering with alien ecosystems, even if we find no evidence of life. Should we proceed with the assumption that we have the right to alter an entire planet to suit our needs? Or should we consider alternative approaches that minimize our impact on the environments we encounter? Similarly, the idea of encountering alien life, whether microbial or intelligent, presents profound ethical questions. How should we approach extraterrestrial life? Should we seek to communicate, study, or even protect it? Or should we focus on ensuring humanity's survival above all else? The discovery of alien life would force us to reconsider our place in the cosmos and confront deep philosophical questions about our role as stewards of the universe. Interstellar travel also presents an opportunity to reflect on the values that will guide humanity as we venture beyond Earth. What kind of civilization do we want to build in the stars? Will we create societies that are equitable, just, and peaceful? Or will we replicate the flaws and inequalities that have defined life on Earth? How will we balance the pursuit of knowledge and exploration with our moral obligations to each other, to the planets we colonize, and to the broader universe? These questions are not abstract. They are questions that will shape the future of humanity as we take our first steps into the cosmos. Ultimately, the psychological, social, and ethical aspects of interstellar travel are just as important as the technological innovations that will make such missions possible. While we focus on developing new propulsion systems, energy sources, and life support technologies, we must also recognize that the success of humanity's journey into the stars depends on our ability to adapt socially, psychologically, and ethically to the challenges of living in space. The legacy of interstellar exploration will not be defined solely by the technology we create or the planets we colonize. It will be defined by the kind of people we become and the values we carry with us as we spread out across the stars. As humanity begins to set its sights on interstellar travel, we must acknowledge that the path ahead will not be easy. The challenges are immense, but the potential rewards are beyond measure. The very act of leaving the comfort of Earth and venturing into the cold, vast expanse of interstellar space will be one of humanity's greatest undertakings. However, one of the key questions that will shape our future as a spacefaring civilization is, what is the true purpose of interstellar exploration? At the heart of this question lies the concept of exploration itself. Throughout history, humanity has been driven by a deep-seated desire to explore the unknown. Whether it was the exploration of new lands on Earth, the vast oceans that separated continents, or the void of space that lies between our planet and the stars, humans have always sought to go farther, to learn more, and to understand the universe in ways that were previously unimaginable. This inherent drive to explore has led to some of the most significant achievements in human history, but interstellar exploration represents the ultimate frontier, one that is beyond anything we have ever attempted before. Interstellar travel is not simply about reaching distant stars or finding new planets to inhabit. It is about advancing human knowledge, expanding our understanding of the universe, and ultimately securing the future of humanity. The vast distances between stars, the unknown risks that lie ahead, and the complexities of sustaining human life over centuries or millennia present obstacles that we cannot yet fully comprehend. Yet these challenges are precisely what make interstellar exploration so compelling. The pursuit of interstellar travel is the pursuit of the unknown, the unfamiliar, and the unknowable. It is the pursuit of answers to the fundamental questions of our existence. What is our place in the universe? Are we alone? What is the ultimate fate of life on Earth? And can we ensure that humanity survives long after the Earth has run its course? To understand the true purpose of interstellar exploration, it's important to consider the existential challenges that face humanity. The most pressing of these challenges is the long-term survival of our species. Earth, as beautiful and abundant as it is not a permanent home. Over the course of billions of years, the sun will continue to burn through its fuel, and eventually it will enter the red giant phase of its life cycle, expanding to a size that will engulf the inner planets, including Earth. While this event is still billions of years away, the idea that humanity is tied to a single planet, one that will eventually become inhospitable, presents an existential crisis. The likelihood of natural disasters, climate change, asteroid impacts, and other catastrophic events that could wipe out humanity is a sobering reality. In order to ensure that humanity survives for the long term, we must look beyond Earth and explore the possibility of establishing permanent colonies on other planets, moons, or even in interstellar space itself. This is where interstellar exploration becomes critical. While the technology to travel to other star systems may seem like a distant dream, it is precisely the pursuit of such a dream that will ultimately ensure the long-term survival of humanity. Establishing colonies on distant planets will not only serve as a backup for the human race in the event of a catastrophe on Earth, but it will also provide humanity with new opportunities for growth, expansion, and discovery. A multiplanetary species will be more resilient, more adaptable, and better equipped to face the challenges of the future. By exploring the stars and finding new homes for humanity, we will safeguard our species against the risks of remaining confined to a single planet. Interstellar exploration also holds the potential to radically transform our understanding of the universe. For millennia, we have gazed up at the stars and wondered about the possibility of life beyond Earth. The search for extraterrestrial intelligence has become a central focus of our scientific endeavors, and the discovery of even microbial life on another planet would have profound implications for our understanding of biology, evolution, and the origins of life itself. But the true discovery that lies at the heart of interstellar exploration is the chance to answer the most profound question humanity has ever asked. Are we alone in the universe? The search for alien life is not just about finding new life forms or encountering extraterrestrial civilizations. It is about understanding our own origins, our place in the cosmos, and the potential for life to exist elsewhere in the universe. If we do find other life forms, what will that mean for our understanding of biology, consciousness, and intelligence? Could we communicate with them? Could we learn from them? These questions challenge our fundamental assumptions about what it means to be alive and conscious, and they open up entirely new possibilities for the future of human civilization. By venturing beyond the confines of our solar system, we will not only discover new planets and stars, but we will also learn more about the nature of life itself, and perhaps uncover insights that will shape our future as a species. However, as we embark on the journey toward interstellar exploration, we must also recognize that the knowledge we gain will be accompanied by great responsibility. The ethical implications of interstellar exploration are vast and multifaceted. If we discover other forms of life, what obligations do we have to protect them? If we find new planets capable of supporting life, how should we approach colonization? The history of human exploration on Earth is marred by the exploitation and destruction of indigenous peoples and ecosystems. As we venture into space, we must ensure that we do not repeat these mistakes. The future of humanity in the stars will be defined not just by our technological achievements, but by our ethical framework, the values and principles we uphold as we encounter new worlds and new forms of life. Moreover, the challenge of interstellar travel requires us to think about the future of human society and governance. The colonization of distant planets will not be the work of a single nation or organization, but a global effort that requires cooperation and collaboration on an unprecedented scale. As we venture into space, we must develop new forms of governance that are capable of managing the complexities of interstellar missions. What will the political systems of space colonies look like? How will they interact with Earth? And how will we ensure that they are sustainable and equitable? These questions will require new forms of diplomacy, international cooperation, and governance, and the solutions we develop will not only impact the future of space exploration, but also shape the future of human society as a whole. Ultimately, the purpose of interstellar exploration is not just about technological advancement or scientific discovery. It is about ensuring that humanity continues to grow, evolve, and thrive for generations to come. The pursuit of interstellar travel is a quest for the future of the human race, a future in which we are no longer bound to a single planet, but are capable of exploring and colonizing the stars. It is a journey of survival, knowledge, and transformation, and it will require the full strength of human ingenuity, creativity, and collaboration. In the end, the true purpose of interstellar exploration is to create a future where humanity is no longer limited by the boundaries of our solar system, but instead is free to explore the universe. It is about answering the fundamental questions of our existence, ensuring the survival of our species, and reaching for a future that is filled with endless possibilities. The challenges we face are daunting, but the rewards are beyond measure. The journey to the stars is one that will define the future of humanity for generations to come, and it is a journey we must begin, not only for ourselves, but for the generations that will follow in our footsteps. As humanity looks to the stars, the task of interstellar exploration presents challenges that transcend the technical and physical, daring us to rethink everything we know about survival, society, and the meaning of human existence. Interstellar travel, while captivating, is a monumental leap into the unknown, and the vast distances between stars create a realm of possibilities and dangers that humanity has never faced before. However, with every challenge comes the potential for transformation, not just in how we travel, but in how we live, learn, and evolve as a species. The long journey into the cosmos is not simply about finding new planets to inhabit or seeking extraterrestrial life. It is about securing humanity's future, pushing the boundaries of what we know, and embracing a bold new chapter in the story of human civilization. At its core, interstellar exploration is a quest for survival, an effort to ensure that humanity, with all its achievements and potential, does not fall victim to the same fate as countless civilizations before it. Earth is our home, but it is a fragile one. In the cosmic scale, our planet is an oasis in a vast, inhospitable universe. Natural disasters, climate change, overpopulation, and other existential threats make it clear that humanity must spread its reach beyond the confines of Earth in order to secure a long-term future. The stars, distant and daunting as they may seem, offer a chance for survival, a cosmic insurance policy of sorts. The knowledge that humanity could one day exist beyond Earth offers hope that we will not simply be an extinct species in the grand sweep of history, but a thriving, spacefaring civilization that has transcended the limitations of a single world. Yet, to achieve this future, we must solve one of the most daunting obstacles humanity has ever faced: the challenge of time. Interstellar distances are immense, and even with advanced propulsion technologies, travel between stars will take decades, centuries, or even millennia. The question is not just how we reach other stars, but how we survive the journey. How do we ensure that human life and civilization can endure for such a long duration in space, isolated from Earth and everything familiar? The answer lies not only in the technology we develop, but in the social, psychological, and philosophical frameworks we create to sustain human life in space. One of the central challenges in long-duration space travel is how to create a self-sustaining environment. Interplanetary missions, such as those to the Moon or Mars, are limited in scope and duration. The resources needed to support astronauts for such missions are relatively small and manageable. But when it comes to interstellar travel, the scale of what is required to sustain life increases exponentially. A spacecraft must be capable of generating its own energy, recycling water, oxygen, and food, and dealing with waste, essentially creating a closed-loop system where everything needed for survival can be produced and consumed without the reliance on Earth-based resources. The concept of bioregenerative life support systems is one promising solution to this challenge. These systems, designed to mimic Earth's natural ecosystems, would involve growing food, purifying air and water, and recycling waste through biological processes. Plants, which produce oxygen through photosynthesis, could play a central role, along with other organisms that help break down waste and provide nutrients. Microorganisms could also help process organic matter and maintain a balanced environment. Such systems are already being tested on Earth in closed environments like the Biosphere 2 project and aboard the International Space Station. However, scaling these systems for interstellar travel, where resources must last for centuries, will require breakthroughs in biotechnology, engineering, and ecological management. Moreover, the long-term psychological impact of living in space must not be underestimated. The confined, artificial environments of spacecraft and the isolation from Earth will place a tremendous strain on the mental and emotional well-being of those aboard. In the short term, astronauts on the International Space Station can rely on communication with loved ones and regular resupply missions to stay connected with Earth. In an interstellar mission, however, the distances will be so great that communication will be limited by the time it takes for signals to travel across space. At best, messages may take years to reach Earth and receive response. The psychological effects of this isolation, combined with the physical strain of microgravity, confinement, and the lack of natural stimuli, could lead to depression, anxiety, and other mental health challenges. To mitigate these effects, interstellar missions will need to focus on providing social support and mental health care. Crews will need to be carefully selected, with individuals who can work well together and manage the stresses of isolation. Social structures will need to be established that promote cooperation, communication, and emotional well-being. Access to entertainment, recreation, and mental stimulation will also be essential for maintaining the crew's psychological health. Virtual reality, for example, could allow astronauts to visit simulated Earth-like environments, offering a psychological escape from the confines of the spacecraft. Additionally, the development of artificial environment spaces designed to mimic the sensations of Earth, with sunlight, green plants, and flowing water, could provide much-needed relief from the sterile, artificial surroundings of the spacecraft. Perhaps the most profound challenge of all, however, lies in the creation of a new society. A successful interstellar mission will not just be about surviving the journey, it will be about thriving as a community. For missions that last centuries or even millennia, humanity will have to evolve in ways that are difficult to predict. The people born aboard generational ships or in colonies on distant planets will grow up in entirely different environments from those on Earth. They will be exposed to different gravitational forces, different atmospheres, and possibly even different forms of radiation. Over time, these environmental factors could lead to physical changes in the human body, and perhaps even to the development of new physiological traits. Humans may become adapted to the conditions of space travel or to the environments of the planets they colonize, creating a new branch of humanity that is biologically distinct from those left behind on Earth. Socially and culturally, interstellar travelers will also undergo a transformation. The concept of Earth as the cradle of humanity may fade into the past as humans spread across the stars, forming new communities and civilizations on distant worlds. These colonies will likely develop their own identities, separate from Earth-based society. Over generations, they may begin to see themselves not as Earthlings, but as citizens of new worlds, separate, independent, and self-sustaining. Language, culture, and even governance may evolve to reflect the unique circumstances of living in space. What will it mean to be human in the vastness of space? How will the ideals and values of Earth shape the new societies of the stars? And what new ethical frameworks will emerge as humanity encounters new environments, challenges, and even alien life? As humanity expands into the stars, we must also consider the broader implications for our understanding of the universe. The search for extraterrestrial life has been a driving force in scientific exploration for centuries. But the true discovery of alien civilizations or life forms is still an unknown. As we venture into new star systems, the discovery of even microbial life would revolutionize our understanding of biology, evolution, and the conditions necessary for life to exist. But the stakes are higher than just scientific discovery. The discovery of alien life would force us reconsider our place in the cosmos, challenge our assumptions about intelligence, and perhaps even compel us to rethink our approach to life ethics and our responsibility to the universe. In addition to the possibility of finding alien life, interstellar travel will also provide humanity with the opportunity to encounter new and uncharted territories. Our exploration of distant star systems will provide us with the tools to better understand the origin and evolution of the universe. It will allow us to witness firsthand the birth and death of stars, the dynamics of galactic formation, and the mysteries of dark matter and dark energy. In doing so, we will answer some of the deepest questions of existence. What is the nature of the cosmos? What is the fate of the universe? And how did life as we know it emerge from the vastness of space? The ultimate purpose of interstellar travel is not just survival, but the expansion of human consciousness, the continuation of our legacy, and the pursuit of knowledge. It is the recognition that humanity, in all its complexity, is a part of something far greater than itself. As we spread across the stars, we will encounter the infinite possibilities of the universe, learn to adapt and grow in ways we cannot yet predict, and create a future where humanity's potential is no longer limited by the confines of Earth. In the end, the journey to the stars is about more than just technology or survival. It is about the unyielding drive to explore, to understand, and to transcend the boundaries of what we thought possible. It is the pursuit of knowledge, the desire to connect with the greater universe, and the understanding that our future as a species is tied to the stars themselves. The challenge is immense, but so is the potential. The road ahead may be long and uncertain, but it is a journey worth undertaking. For in exploring the stars, we are ultimately exploring ourselves. As we push forward into the unknown realms of space, with interstellar travel becoming an increasingly tangible aspiration for humanity, we must take a step back and examine the broader picture. What will this monumental leap into the cosmos mean for the very fabric of human existence? The ambition to reach other star systems represents more than just an engineering challenge. It signifies a deep existential shift, one that will reshape our species in ways we can barely begin to imagine. As we venture beyond Earth, what will it mean to be human, and how will our civilization evolve as we spread throughout the galaxy? The future of interstellar travel is ultimately about much more than technology and exploration. It is about what kind of legacy we leave for future generations, and how we define our place in the universe. The initial stages of humanity's journey into the stars will undoubtedly be dominated by a sense of awe, curiosity, and adventure. The first interstellar probes will be symbols of human ingenuity, miniature spacecraft carrying the hopes and dreams of Earth as they journey into the unknown. These probes will be our first ambassadors, gathering invaluable data about distant star systems, searching for habitable planets, and investigating the possibility of alien life. With projects like Breakthrough Starshot already underway, this next step will be the beginning of humanity's transformation into a spacefaring civilization. However, the deeper significance of these endeavors goes far beyond the data they will return or the planets they might discover. These missions will mark the first steps in humanity's broader migration into the cosmos, and the implications of this migration will be profound. At the heart of this migration is the idea of securing humanity's future. Earth, our home for millennia, is not impervious to disaster, whether caused by natural events like asteroid impacts, supervolcanoes, or the eventual exploration of the sun, or the result of human-made crises like climate change or nuclear warfare. There is always the possibility that humanity could face extinction on this single planet. The drive for interstellar travel, in part, represents a quest for survival, a contingency plan that could ensure the continuation of human life beyond Earth. The challenge is, of course, staggering. The vast distances between stars, the unknown dangers of space, the difficulty in creating self-sustaining systems that can support life for centuries or millennia. All of these factors make interstellar travel one of the greatest challenges humanity will ever face. But it is also the greatest opportunity we will have to secure the survival of our species. Colonizing other planets or moons, or even establishing self-sustaining habitats in deep space, will reduce the risk of extinction by ensuring that humanity is not confined to a single vulnerable world. But survival is only one part of the story. The true transformative power of interstellar travel lies in its ability to unlock a new era of human expansion. Just as humans once moved from their African origins to inhabit every continent on Earth, so too will we eventually spread throughout the galaxy, exploring, settling and transforming distant star systems. This expansion will not simply be about survival, but about growth. Growth of the human experience, of human culture, and of the very essence of what it means to be human. Our existence, as it is currently confined to Earth, has limitations, whether they are social, economic, cultural, or physical. As we venture into space, we will encounter new environments, new challenges, and new opportunities that will radically alter how we perceive ourselves and our place in the cosmos. This transformation will be felt on a deeply individual level. Living in space, particularly on distant planets, will require humans to adapt physically and mentally in ways that we cannot yet fully predict. Gravity, atmosphere, radiation levels, and the availability of resources will shape human biology in ways we are only beginning to understand. Over generations, the children born in space or on other planets could develop distinct physiological differences from Earth dwellers. In a low-gravity environment, for example, bones may become more brittle, muscles weaker, and the cardiovascular system could function differently. Alternatively, in a higher gravity environment, humans may evolve to be more robust, with stronger bones and muscles to withstand the additional pressure. The psychological and emotional adaptations required to cope with the isolation and confinement of interstellar travel will also lead to new ways of thinking about identity and community. The boundaries of what it means to be human may expand as humanity adapts to living in new environments, becoming not just Earthlings but spacefarers with distinct cultures, languages, and identity. For those living in space or on other planets, the concept of home will likely undergo a radical transformation. Earth will always be the place of origin, the cradle of humanity, but the idea of home may evolve as people spend generations in the depths of space. As humanity spreads to the stars, people will begin to identify not just with their home planet, but also with the new worlds they inhabit. A child born on a colony on Mars or on a spacecraft traveling toward a distant star will have a completely different sense of identity than someone born on Earth. Over generations, these colonies will develop their own cultures, traditions, and even governance structures that reflect their unique environment and history. Humanity as a spacefaring species will become diverse in ways we cannot yet fully grasp. Earth will still be home to the original humanity, but the people of the stars will carry forward a new vision of what it means to be human. But even as humanity expands, questions of ethics and governance will become more complex. As we begin to colonize distant planets and moons, we will face the moral dilemma of how to interact with any potential life we may encounter. For example, if we discover microbial life on a distant world, should we preserve it at all costs? Or should we prioritize human needs and colonization? The answer is far from simple, and the ethical considerations of space colonization will likely require new frameworks of international law, ethics, and diplomacy. Colonizing planets and moons that may have ecosystems of their own brings up questions about whether humanity has the right to alter or terraform these environments to suit our needs. Additionally, how will the governance of interstellar colonies be managed? Will these colonies remain under the jurisdiction of Earth-based nations, or will they develop their own political systems and governance structures? These questions will need to be addressed in a way that reflects both the interests of humanity and the rights of the ecosystems and life forms we may encounter. Furthermore, as we expand into space, resource management will become a central concern. Interstellar travel will require immense amounts of energy, materials, and infrastructure to sustain life over long periods. As we begin to establish colonies, the demand for resources will increase, creating new challenges in terms of mining, manufacturing, and ensuring that these resources are distributed equitably across spacefaring colonies. The technology to mine asteroids, extract water from distant moons, and harness the energy of stars will be crucial to sustaining human life in space. However, the economics of space resource extraction will require new global or perhaps interstellar systems of trade, distribution, and governance. The social and psychological dynamics of living in space will also evolve. Early interstellar settlers will likely come from a wide range of backgrounds and cultures, bringing their own ideas, traditions, and expectations with them. Over time, as these settlers form new societies, they may develop their own identities, distinct from Earth-based civilizations. This could lead to the creation of unique spacefaring cultures, with their own languages, customs, and ways of life. The challenge will be to foster cooperation between different colonies, and perhaps even between the people on Earth and the people living in space. The long-term success of humanity's expansion into space will depend not only on technological progress, but on how we handle the social, cultural, and political challenges that arise as we become a multiplanetary species. In the broader context of interstellar travel, the very meaning of exploration will shift. While exploration has always been about discovering the unknown, expanding our knowledge, and challenging the boundaries of our existence, interstellar exploration will introduce entirely new dimensions to this quest. As we push into distant star systems, the exploration of the cosmos will take on not just a scientific purpose, but also a deeply existential one. We will not just be uncovering the mysteries of distant stars and planets, but also redefining what it means to be human. The very act of venturing beyond our solar system will force us to confront the nature of life, intelligence, and consciousness. What does it mean to be alive? And how can we maintain our humanity as we spread across the universe? Ultimately, the success of humanity's venture into the stars will depend on our ability to adapt to new technologies, new environments, and new ways of thinking about who we are. The journey will be one of transformation, not just technologically, but spiritually, culturally, and philosophically. It is a journey that will shape the future of our species, guiding us to a future where humanity is no longer confined to a single planet, but free to explore and settle across the stars. The challenges are vast, but so too are the opportunity. As we continue to reach for the stars, we will discover not just new worlds, but new possibilities for growth, survival, and understanding. It is a future worth striving for, and it is a future that is within our grasp. As we stand at the threshold of interstellar exploration, the possibilities before us are awe-inspiring, yet the road ahead is fraught with immense challenges. Interstellar travel represents humanity's boldest and most ambitious endeavor, one that transcends the boundaries of technology, science, and even philosophy. The very act of venturing into the cosmos to explore other star systems, to find new planets for habitation, and to ensure humanity's survival beyond Earth is not just an extension of human curiosity, it is the next critical step in the evolution of our species. While we may not be able to fully envision the future of interstellar travel, what is certain is that the journey itself will reshape our civilization in ways that will define the trajectory of humanity for centuries, if not millennia. The quest to reach the stars is driven by a fundamental desire to survive and to thrive. Earth, as our only home, is vulnerable, its resources finite, its future uncertain. Interstellar travel offers us a backup plan, a potential escape from the existential threats that loom over us. Whether through natural catastrophes like asteroid impacts or man-made challenges like climate change, humanity faces risks that could jeopardize our survival. Establishing colonies on other planets or moons, or even venturing into the vastness of space itself, offers an opportunity to spread human civilization across multiple worlds, making us more resilient and ensuring the long-term survival of the species. However, survival is only one aspect of interstellar exploration. The endeavor will also redefine our identity as humans. The challenge of traveling to another star system and establishing colonies will force humanity to confront fundamental questions about what it means to be human. The process will undoubtedly change us, not just technologically or physically, but socially, culturally, and ethically. The people who will live aboard spacecraft or on distant planets will face completely different circumstances from those of us on Earth. Over generations, they will adapt to new environments, different gravitational forces, and entirely different ways of life. Over time, they may even evolve biologically and psychologically into something distinct from Earth-based humans. But despite these changes, the essence of humanity, the quest for knowledge, survival, connection, and growth, will remain the guiding force of our existence. At the same time, as we reach for the stars, we must approach this monumental challenge with great responsibility. The ethical implications of interstellar colonization and exploration are profound and complex. From the discovery of alien life to the potential to terraform other planets, We will face difficult decisions that challenge our notions of stewardship, governance, and morality. Will we respect the integrity of planets and moons we encounter, or will we view them as mere resources for human exploitation? How will we balance the pursuit of scientific knowledge with the protection of life, whether microbial or more advanced, that we may find on other worlds? These questions will shape not just the success of interstellar missions, but the values and principles that guide humanity as a spacefaring civilization. Moreover, the success of humanity in the stars will depend not only on overcoming technical challenges, but on fostering cooperation and unity. In the vacuum of space, there will be no room for division or conflict based on national borders, race, or ideology. The future of humanity in space will be a global endeavor, one that requires collective effort, shared knowledge, and collaboration. Whether we are building the technologies needed for interstellar travel, or designing the social systems that will govern life aboard generational ships or on distant colonies, we will need to work together in ways that transcend our division. In many ways, interstellar exploration will force humanity to reimagine its social structures and relationships, making unity and cooperation not just idealistic goals, but necessities for success. As we look ahead, the potential for interstellar exploration is both exhilarating and daunting. We are only at the very beginning of this journey, but the progress we make today will lay the foundation for future generations. The steps we take now in terms of research, technology, ethics, and collaboration will determine the shape of humanity's future in the cosmos. The challenges are immense: distances, time, resources, and the unknown dangers of space. But the rewards are equally profound. The discovery of new worlds, the possibility of meeting alien civilizations, and the chance to secure the long-term survival of humanity are just a few of the extraordinary benefits that await us. In the end, interstellar travel is not just about exploring new frontiers in space. It is about exploring the potential within ourselves. It is a journey that will require us to push the limits of what we thought was possible, to adapt to new realities, and to evolve as a species. The journey to the stars will be as much about transforming humanity as it is about transforming the universe around us. The questions we ask, the values we uphold, and the choices we make along the way will shape the legacy of humanity for generations to come. And while the road ahead may be long and filled with uncertainties, it is a journey worth undertaking, a journey that will ultimately define who we are, where we go, and what we become as we venture out into the stars.